Hello and welcome to Coronacast 2024. My name is Catherine Wilbanks, and we are a joint student-led cooperation between the University of Michigan's Climate and Space Sciences program and UTA's, the University of Texas at Arlington's, Physics Department. And we've been modeling what we're hoping to observe today during the total solar eclipse, the outer edge of the sun's atmosphere, the corona. But I've not been working alone here. I've been working with a team of excellent scientists that are also in the room with me. So why don't you guys all say hi?
Hi.
Hi.
Hello.
And a quick introduction, names and positions.
Hi everyone, I'm Sharon Liu, first year PhD student from University of Michigan. And in the simulation side, I'm using the numerical simulation of the solar corona and generate the output for our eclipse predictions.
Hi, everyone. My name is Hao Liu. I'm a second-year PhD student at the University of Michigan. I'm doing the solar and hemispheric physics. I'm also doing the simulations in this project.
Hello, Chip Manchester. I'm a research professor at the University of Michigan. I primarily work in solar physics, coronal mass ejection, steady-state corona, and just basically helping advise the students here.
I'm Amy Rewalt. I'm a second-year graduate student in the Department of Climate and Space at U of M. I primarily work on magnetosphere physics, but in this project I've been working with graphics and just picking up any loose ends that we may need to take care of.
And leaning in the picture here, I'm Dan Welling. I'm a University of Michigan assistant professor. I've been help organize things, and giving the students support where they need it throughout this project. And I'm going to duck out back out of camera.
Yeah, so we have been working hard the last several months to get our models up to snuff so that way we can produce wonderful predictions for you. We're actually going to go through those predictions a little bit together through the room. So can we get our current forecast up on the stream?
You bet. And what we're going to do, right now the rotating slide with our predictions is on the screen, but I'm going to go ahead and switch to our PowerPoint with the results as soon as I get that up. So, excuse me, we have a lot of controls going up. And there we go.
So these are our latest forecast predictions for the solar eclipse later this afternoon. I'm actually going to toss it over to the other side of the room so that way you guys can walk us through exactly what these images are showing and what we're hoping to see later today.
So right now I got the white light images up. Sorry, Sean, do you want to talk a little bit about the white light images? Alright, so the white light images are basically what our naked eye can see during the eclipse. So there are actually some scattering of the light from the solar surface, and then the later scatter from the solar corona and getting to the Earth. So we're now synthesize the white light signals from our model as presented here, and you can see the large-scale structures stretching out, and some dark regions, some bright regions, indicate different structures in the solar corona, and they're highly aligned with the structure of the magnetic field. And the next slide we have is polarized brightness, but we can skip that, or if you want to talk through that one. So the polarized brightness is actually very similar to the total brightness. It's just a kind of different component of the white light. It's a subtraction of the signals in one direction to the other direction, and it's more contrast in its image than the total brightness, so we can more clearly see the structures at the corona. And now the coronal emission lines. So the coronal emission lines are basically emitted by some ions existing in the solar corona. So in the solar corona, the temperature is extremely high, and all the ions are fully ionized, and a lot of spectral lines at specific wavelengths are generated by the collisions of all these ions. So now we're seeing the combination of several spectral lines with different sensitivities to the solar corona condition and different distributions and different structures. So we can see different colors in different places of the sun. And there's those regions that are blue, that the temperature is lower. And when we go to green and the red color, we can see that the temperature in those structures are getting hotter.
And now the magnetic field visualizations, which are some of my favorites.
Yeah,
We
my
have
favorite
both
too,
the
yeah.
close in and the zoomed out ones on screen right now.
Yeah, so there are basically some 3D rendering of the magnetic field structures in the solar corona. And we calculate some variables associated with the magnetic field and do the integration in the whole 3D space and presenting the whole 3D structure in the 2D images in front of us. And we can see how the magnetic field lines are originated from some specific regions and get connected and stretching out in the further solar corona. And we can see a large differences between different models. So we can see different structures like streamers, some closed loops, and active regions and corona holes.
And then finally, the extreme ultraviolet images.
Yeah, so extreme ultraviolet images are actually a very important signal that we can learn about the solar corona. And so, as we know that the solar corona is very, very hot and they're emitting extremely short wavelength signals in the solar corona. So as we know, as a extreme ultraviolet, and our naked eyes cannot see the signals, but we have the satellites and some telescopes specifically used to observe this kind of signals, and they tell us a lot information about the solar corona's temperature and density.
We're hoping that some of these images actually correspond with what we're going to see later today, but I believe we already have the Detroit Observatory on call, ready to talk to us. So we're going to jump on over to a Zoom call with them as we talk about what exactly is an eclipse and what we are hoping to see later today, barring cloud coverage for most of the path of totality.
And given that this is a live stream, just give me 2 seconds to make sure everybody can hear us. Austin, if you want to unmute and talk and make sure we can hear you.
Yeah. Hello. Can you hear us?
Yes, we can. Do you actually mind boosting my audio up a little bit?
Yeah, no problem.
Thanks so much for joining us. Do you mind
Yeah.
introducing yourselves and telling us where you're calling in from?
Yeah, so we're originally from the Detroit Observatory in Ann Arbor, Michigan. We're part of the University of Michigan. And I am Austin Edmister. I'm the Assistant Director for Astronomy. And then with me, I have 3 astronomy docents, and I'll let them introduce themselves. So,
My name's Jonathan Meadows. I'm an astronomy docent and a second year at the University of Michigan.
My name's Leyland Borum. I'm an astronomy docent and I'm a 4th year at U of M.
I'm Katja Guzman. I'm a PhD student, 4th year in the astronomy department in Michigan.
Great.
and right now we're in Troy, Ohio. We're visiting a friend of the Bentley Historical Library who has offered us some land to hang out on and try to observe the eclipse. So we're pretty excited about that.
That sounds fantastic. How are y'all's clouds looking for today?
Wispy.
Clear, you can see through them. So I think, regardless, I think we're going to see the eclipse. I think it'll just be, are we seeing it through wispy clouds or a totally clear sky? But I think we're going to see it.
Fantastic. I think we're sitting in a very similar boat. So the first kind of question that I had for you guys is, what exactly is an eclipse? What are we going to be seeing later today?
So the total solar eclipse is going to be the moon, the dark circle of the new moon completely blocking the sun. And this total solar eclipse allows you to see parts of the sun that you don't normally see. So while you're in the shadow of the moon, you can also see the corona of the sun. It's sort of like, putting up your hand against a bright light, or if you're driving down the road, you might have some headlights, and if you block those, the things around it get easier to see, including the solar corona, which is this upper atmosphere. So we're excited to see this solar corona that you don't normally see with your own eyes.
Yeah, and that's exactly what we've been modeling here for this past week, and we're hoping those observations match exactly what we've been modeling. So what exactly is so special about this eclipse in particular? There's been a bunch of hype around it. A lot of people are saying this is a great opportunity. What's making this one so much more special than the ones that we've had in the past?
I think primarily it's positioning, and kind of going all around the world, you have eclipses happening a lot of the time, but you have them in the ocean, you have them in other countries, and they're not super available for everybody. But this one's really cool because the fact that it's kind of cutting right through the east side of the U.S. So you have around 200 million people who are within driving distance of the eclipse. So it's a great opportunity for the people to actually come and see it.
Yeah, it's a fantastic opportunity. In fact, it's coming through my hometown here in Arlington. So we're really excited about it. So there was actually an eclipse that came through Texas last year. I believe it was an annular eclipse. Can you kind of talk us through what's the difference between that one that a lot of Texans saw last year and this one? And what's the difference between the people who are going to be in the path of totality and outside the path of totality?
So the eclipses come in different flavors because the moon has a not perfect circle orbit around the Earth. That orbit is slightly elliptical. The moon can get slightly closer to us and slightly further away.
Mm-hmm.
So when it's an annular eclipse, the moon is a little bit closer to us in its orbit, and it can't completely cover the disk of the sun. So those are our annular eclipses, and they're often called a ring of fire. So when you hear the frequency of solar eclipses, it includes partials, it includes annular eclipses, and it includes total eclipses like today.
Fantastic. So another question that I have, a lot of people have been hesitant about driving into the path of totality and are saying they're fine with being at 90% of a partial eclipse or 99%. What's that extra percentage going to get them? Is it worth the drive?
100%.
100%.
Yes, everything.
Yeah.
The difference between 99 and 100.
Yeah.
If it's not totality, you always have to look through eclipse glasses. Like, you can't ever take them off because there's always a section of the sun that could, burn your eyes.
Mm-hmm.
But in totality, you can take off your glasses, you could stare directly out there, and it's absolutely beautiful sight to see just the black disk of the moon and the solar corona around it.
A phrase that comes to mind is the difference between 99% and 100% is 100%. It's completely different.
That's very true.
Yeah.
So speaking of eclipse glasses, there's been a lot of talk about when to put them on, when to take them off. Can you kind of walk people through when they should be wearing their eclipse glasses, when it's safe to take them off?
Yes, I'm all about eclipse safety. I do a lot of solar observing, so you're right on topic for me.
Great.
Pretty much everywhere up until totality, you want to keep your solar eclipse glasses on, right? If you can see even a little bit of the sun through your solar eclipse glasses, that's still sunlight that can harm your eyes. Once the sun totally disappears in your solar eclipse glasses, it is relatively safe to take off your solar eclipse glasses and see the total. However, I do caution that right at the beginning of the solar eclipse, the total eclipse, and right at the end, there are points where the sun's light can peek out around the edge of the moon, like around mountains, around craters, and that can still also be a little harmful to your eyes. So the solar eclipse glasses are great up into the total and after the total, and also right there at the moment of change. So you want to keep them on right at those moments, and then once things are totally safe, you can take them off.
Fantastic. So I've actually been talking to a lot of local students here in Arlington, and probably the number one asked question that I got in the past couple days was, is it safe for my pets to be outside during a total solar eclipse? So I'm kind of curious what y'all's answer is to that as well.
We're not vet professionals.
That was often my answer too.
Yeah, I often lead towards caution. So don't, you as a human, of course, don't look at the sun without solar eclipse glasses. But also, if you do, what you don't want to do is force your pets to watch the eclipse, right? Like, you don't want to hold their face up to it. You don't want to put the glasses on them because the glasses might not fit appropriately for the eclipse. So animals know not to stare at the sun. They have the same instincts as us. It hurts your eyes. So just don't force them to watch the eclipse, and they'll be fine. I've never had a problem with having pets out during an eclipse.
Yeah, excellent suggestion. So moving on to exactly what you guys do at the Detroit Observatory, can you kind of talk us through what y'all's missions are, what y'all typically observe?
Yeah, so I guess at the observatory, one of the main goals we have is just outreach. We just opened recently in 2022 with the start of the docent program, which is what the three of us are a part of. And I guess what we typically do week to week basis is that people come in And we give them tours of the Detroit Observatory. We tell them the history, how it was founded, and what research purposes it served. There's a history of timekeeping at the observatory that serviced many parts in the Midwest that we like to talk about a lot because not many people know about it. And then on nights when it's clear, which, Michigan weather, it's kind of a 50-50 chance. It's not that common. But when it is clear, we do like to still give people the chance to observe. So with our 1857 Henry Fitz telescope, we like to observe with that. That's still in use today. And then we have smaller but more modern telescopes that we like to use as well. And sort of trying to show people the connection at the observatory that we have between history and astronomy. Yeah, it's really cool.
Yeah,
And I do want to add. Oh, sorry, Amy.
No, go ahead.
Well, I do want to add too. Part of our history is going on eclipse expeditions. So Detroit Observatory astronomers 160 years ago, 150 years ago, 120 years ago, 100 years ago, they were doing eclipse trips around the nation. They visited all over the nation. And a few times they even traveled internationally to observe eclipses. So we're also in a way trying to carry on that tradition of, traveling for an eclipse to record it and experience it. And I think that's going so far pretty well.
Yeah, I think so too. So you were talking about how how you have a history of traveling into eclipse path. What specifically are your group hoping to observe this year? And are you guys using any specialized equipment?
So we're bringing along two primary things. Two things. We have a solar H-alpha telescope, a telescope designed to look at the lower atmosphere of the sun, the chromosphere. However, with wispy clouds like today, we'll see what actually happens, but we'll be trying for H-alpha views of the sun. We will also be using a traditional digital camera that has a long zoom lens and a special filter to protect from the sunlight. And we will be taking photographs, hopefully, of the solar corona and then the wider space around it. There are a few stars we want to look at around it and see if we can capture those stars. We're also interested in maybe photographing the comet that is currently high in the sky right now near the sun. So that'll be really interesting if we can capture that. And then once we have these pictures made, we're hoping to pass them on to a few students at the University of Michigan so that they can use for their corona forecasts.
Such as us. So you were actually talking about some of the stars that you can see during the eclipse. What stars in particular are you looking out for, and what other celestial bodies will people be able to see during totality?
I believe it's Pisces, if I'm correct. Yep. The sun is in Pisces, so we're looking for a few stars around that. And forgive me if I'm wrong, that's just what I remember at the moment. And then Jupiter is high in the sky. Jupiter will be so bright. It will, we've been following Jupiter as it gets closer and closer to the setting sun. Well, now we don't have to worry about that today. If the sun goes away, Jupiter comes out during the daytime. The comet, of course. And I think that's, if I'm missing anything, but I think that's most of our key goals. We're also just hoping to enjoy it, right? So we have some plans. We want to also to just enjoy the eclipse because that can often be the most important experience.
Oh, absolutely. I'm actually really looking forward. This is the first time that I should be able to see totality. So I'm really looking forward to enjoying it. But I believe someone else was about to say something.
Katya?
Oh, I was going to say, and I mean, take this chance while you can, because we won't get one of these total solar eclipses for a while in the U.S.
Yeah, exactly. You were leading me right into my next question. How rare are these for the United States or for a particular place, and when will we see our next one?
Yeah. So I think in the U.S. we've had, I guess for the kind of total solar eclipse we're having now, not the annular one, we had another one back in 2017 in August that also a lot of the United States was able to see that the two paths kind of crisscross. The one from 2017 kind of went from the Pacific Northwest and downward, and this one is going up towards the northeast of the U.S. So they're kind of doing, where's the camera? And then the next one won't actually be until August of 2044. So that's in
18 years.
18.
I believe that'll be Nebraska.
20 years?
Not Nebraska, North Dakota.
18 years.
2044.
Yeah.
2044. Oh, that is 20 years. 20 years.
Yeah, 2044. And I mean, it, I guess, varies location by location as to where they're more common. I think they're more common in the northern hemisphere, possibly, than the southern.
The eclipses tend to crisscross across, over the entire surface of the Earth.
Mm-hmm.
They are somewhat cyclical over periods of 9 and 18 and longer years. And so some of these eclipses tend to repeat over, a century. And so over the 21st century, there will be more repetitions of eclipses across the United States. They'll be slightly different in different positions, but after 2044, I think every 10 or so years they start to pick up again, and then there'll be another large gap.
I think there's going to be a major one in Europe, like in the Spain region, relatively recent, like relatively soon.
Yes, I believe the next total solar eclipse.
Yeah.
Yeah,
but there won't be one in the U.S. for a while.
There won't. But the next total solar eclipse is going to be in August of 2026, and it's going to actually pass through part of the Arctic, Greenland, and Spain. Is probably the best place for people to get a glimpse of it.
Mm-hmm.
So I also wanted to ask you about some of the science that we can learn during eclipses. I mean, there's a bunch of astronomers, heliophysicists or solar physicists like us that have traveled into the path of totality, and we're all hoping to learn a lot during an event like an eclipse. What are some of the things that we can learn during total solar eclipses?
Something interesting that came up recently, there was a talk at our observatory from a student at Eastern Michigan University, and they are using a high altitude balloon to measure the change in kind of like we think of like ocean waves, but in the air. They're called gravitational waves or gravity waves, not like the gravitational waves with lasers, but these gravity waves in the air. They're like measuring changes in the atmosphere from a solar eclipse with a high altitude balloon. So I think that's like the wildest thing. That's like, oh yeah, that makes sense.
That sounds pretty crazy.
That's happening. I think we're hoping to see if we can do like a really light test of
gravitational lensing.
Yeah, gravitational lensing of like stars near the sun. Like, if we take pictures of certain stars, can we measure their lateral distance from each other?
I mean, eclipse was used to kind of confirm Einstein's theory of relativity, which is what lensing is, like the physics is based on. Back in the early 1900s. I think it was an eclipse expedition to Africa that Sir Arthur Eddington did, in order to kind of see if they could calculate or see the deflection of starlight, which you can really only see during an eclipse, because other than that, it's so bright around the sun, you can't see any of the stars.
You guys are doing great at leading me right into my next questions that I have for y'all. So what's some of the, as you just mentioned, Eddington kind of confirming special relativity during a total solar eclipse. What are some of the other unique historical or just history behind total solar eclipses?
For me personally, the Detroit Observatory and Michigan observatories actually have an interesting history of eclipses sort of leading to new things for us. So there was an eclipse, I believe, in 1924, and I'm terribly remembering where it was. I get it mixed up with our other ones. But at this eclipse, there were 3 people that attended a hot air balloon observation of the eclipse, and it was totally cloudy. But what did they do on a cloudy day in a hot air balloon? They started talking shop. And these people, this group of people from the observatory and some amateur astronomers, ended up starting an observatory almost out of conversations from this eclipse that they traveled to. And that was the McMath-Holbert Solar Observatory. So for us, like just going to eclipses have led to, new things for us. We also have a really, and one of you might want to tell the story, but one of our astronomers from the 19th century went to an eclipse and didn't really make a good discovery, but more of a blunder. And I don't know if anyone
Oh my.
Yeah, in the one of our directors at the observatory, his name was James C. Watson, and he was an extraordinarily smart man, but he had a bit of an obsession about finding this planet that didn't really exist, Vulcan. It was supposed to be a planet that existed between Mercury and the Sun, and he thought that during a total solar eclipse like this, he would be able to document it and finally prove once and for all, like, hey, boom, there's another planet right there.
And I believe in one of his charts, he did mark it down. But nobody else could confirm that that was actually there, and nobody really knows what he saw. Maybe it was a comet or some rogue asteroid, but that was just a bit of an interesting history with one of our directors in the past at the Detroit Observatory.
That's such a fascinating story to me. But I also wanted to ask you guys about your own personal history with total solar eclipses. Have you guys seen them in the past? What are some of your favorite experiences seeing them, if you have? And what are you looking forward to, especially with this one this year?
I mean, I went to go see the one in 2017. I'm originally from the Chicago area, and so I went with some friends down to Southern Illinois to, I think it was Benton, near Rend Lake. We, found a little park there. We had a little picnic. It was very nice. It was in August, so it was summertime. And it was perfectly clear. Like there were no clouds. We didn't have any of the wisps we're having today, and it was pretty awesome. The one thing is we did not have a telescope with us, so I'm very excited to see this through an actual telescope this time, because before I just had my eclipse glasses and little pinhole projector.
Yeah, and I guess also the one in 2017, I was in Detroit, so it was kind of like a partial eclipse for me. And my only experience was I stacked two sunglasses on top of each other. I did not look at the sun, but I used my phone camera to try to get a photo of the sun through the two sunglasses, and it actually kind of worked. But that is my only experience. This is going to be my first total solar eclipse. I am excited, but yeah.
I went down to Kentucky to watch the one in 2017, and it was pretty cloudy, and half of it got covered up during totality.
Oh, no.
So it's kind of an experience that got shunted a little bit. So I'm excited, and I'm hoping that that doesn't happen this year. Plus, with all the equipment that we have with us, I'm sure we're going to get some great pictures.
And then all of my family is Southern Illinois, and that's where I'm from. So for 2017, I brought along a lot of my friends from college and grad school at the time down to Southern Illinois. We camped outside my sister's house. It was like a little farm in the middle of nowhere. And then we went to my dad's house. My dad lived exactly under the totality line.
Oh, wow.
So we got about 2 minutes and 20 seconds of the total eclipse, and it was just wonderful. It was a blistering hot day, and it was like 95% humidity, but it was a fantastic experience. And I think, like Katya, we had a totally clear view. It was really lucky because we had clouds on both sides, but it was a very memorable experience. So I'm looking forward to sharing that with this crew this time.
Yeah, hopefully the weather holds up. We are all crossing our fingers for some breaks in the clouds.
We just keep saying, we're going to see the eclipse. We're going to see the eclipse. We're going to see it.
No matter what, we're going to see it. So we've talked a little bit about histories of eclipses, how they occur, y'all's personal experiences, what y'all are observing. But for the general person, as they're out watching the total solar eclipse, what are some of the phenomena that they're going to experience throughout the whole process?
I think one of the ones that are pretty cool and maybe not people don't think about too much is the fact that obviously it is going to get a bit darker, but it's also going to get colder too, by about 3 degrees, and that's a noticeable change. I think that's really fun. It's like, ooh, a little cold outside, especially with how hot it is going to be today.
I remember very distinctly at the 2017 eclipse, because it was so hot that day. It was like this relief for, you were enjoying the eclipse, but it was also just nicer out. And then when the eclipse was done, the sun came back with a fury, and it was just it was so hot. But that temperature change is part of it. It's just like there's so many sensory things happening. An eclipse is such a sensory experience. You're hearing things, like you might hear like birds start to talk, or animals moving and stuff like that. There's just so much happening. You got to take it all in.
For sure, absolutely. I think one of my favorite phenomena is actually Bailey's beads. I'm looking forward to hopefully seeing some of those. Do you think one of you guys could kind of talk about what's happening there with Bailey's beads, when people can expect to see them?
Yeah, so don't ask me who Bailey is. I don't know them. But the beads are sort of a phenomenon where, the imperfection
around the moon's circle allow sunlight to come through between craters, between mountains, and they're actually, it's one of those things. Bailey beads are, it's not perfectly safe to look at with your naked eye, so do be careful if you do look at Bailey's beads, or try to use solar eclipse glasses if they're bright. But it's just peaks of sunlight sort of looking around the moon and reaching the Earth. And I think that really kind of defines how the moon is a rock in space. It's not just someone holding up a circle. It is a rock in space. And so it's imperfect, and you get to see that. And it's kind of different each time, has how each eclipse is different. Each time the moon, the connections of the perimeter of the moon with the perimeter of the sun are going to be slightly different between different eclipses. And so sometimes you just get different patterns of Bailey beads. Like a lot of eclipse chasers, they've seen the corona so many times they couldn't care. They're all about Bailey's beads. But it's like a totally different thing to look for.
For sure. I'm so excited to finally see them, because that just absolutely blows my mind that we're seeing effects due to the surface of the moon. I think you kind of mentioned it already, but observing the corona during a total solar eclipse, what exactly are we seeing, and how is that unique for total solar eclipses?
Usually you can't see the corona when you're looking at the sun because the rest of it is so bright. But now, because most of the sun is completely blocked, now you can sort of see the very outer part of the sun. And the corona is interesting because that's also where you get things like coronal mass ejections, for example, which are these really powerful, what are they called? Emissions, I guess, of plasma that come from the sun. The sun is very highly magnetically active. Yeah, that was a word. And because of that, it's got magnetic field lines. They all get twisted sometimes. And so you start seeing things like prominence, like these arcs of plasma. And sometimes they can be flung out into space. And so those are called coronal mass ejections. Sometimes they reach Earth. If they're powerful enough, they can cause things like aurora in the northern or southern hemispheres. So like the aurora borealis or australis, depending on where you are. Sometimes they can even cause power outages or more damage to that extent. But yeah.
I think something that's special to me too is I think as children, probably all of us drew the sun with fire around the edge, or with like big flames coming off. And then when we show someone the sun through like a white light view, like during the day we have solar telescope viewing or something like that, it's just such a perfect circle almost. It's like some people don't even realize that they're looking at the entire sun because it's such a perfect circle. And they're like, oh, I expected there to be a lot going on. It's like, well, there is. It's just you can't see it right now. But during an eclipse, it's all there, just like all the details and all the imperfections or changes. It just becomes a much more dynamic object than just a perfect circle in the sky.
Yeah, and especially with where we'll talk more about this in our next segment, but especially with where we are at in the solar cycle, we're kind of expecting to see a lot of structure in the corona this year, correct?
Well, we're not solar experts, but I think, we're near a solar maximum, so a lot more stuff is happening on the surface. At the observatory, when we've been doing solar observing, we've been seeing enormous sunspots, prominences. It's been a really fun year because we've gotten a lot to look at. So I'm hoping that's going to mean a really busy corona. And the predictions that were shown before, I think, are really exciting because that looks like a lot going on.
Yeah, we've got a lot of structure coming out of our suns and our predictions, and we're hoping they match up to observations like the observations that you guys are going to be making later today. What are some of the fun and interesting projects that the Detroit Observatory is doing currently?
So we've got so much going on right now. I mean, we're this historical observatory with these wonderful collections of astronomical instruments. And I guess to stop before I go too long, are you talking about today or in general?
In general, if people wanted to
in general, okay. Just before I give you the answer you didn't ask for. So we're doing a lot. We're doing a lot with telescope observing. We have specialized telescopes for looking at the sun. One of them that we brought with us today. The docents are always creating fantastic talks. In fact, Katya is giving a talk on U of M astronauts in about a week, and less than a week, Friday. We've got tours through our historic observatory. We're looking to do more outreach this summer. And so many things are happening. And we've got exhibits. We've got a wonderful collection of smaller items that we're building exhibits around. Mm-hmm. Just so much. And we do stuff almost every Friday and most Thursdays. We have special talks. We have hands-on things that we do that are a lot of fun. So it's just starting up workshops. We're starting up workshops. We're doing like astrophotography workshops. We're working on building like telescope workshops or even astronomical sketching workshops down the line. So we really want to engage people with the type of history and contemporary astronomy that we do at the observatory.
That sounds fantastic. I'm gonna have to come by way more often. Why don't you guys let people know where they can find you, where you're located, social media, etc., etc.
We don't have a lot of social media right now. We're working on it, but you can find us on our website at the Detroit Observatory. That's where we headquarters almost all of our information. You can find more about us as well. We're part of the Bentley Historical Library, oddly enough. We're part of an archive. We're kind of like the 3D archive of the Bentley. And you can find us across campus and on the observatory. So we're usually doing things. And the website's usually the best place to go right now.
All right.
We have a Facebook, but we understand this.
Yeah, for sure. Feel free to drop the link for y'all's website in the chat, and we can get that out to people if they're interested in dropping by for a visit. But other than that, you guys have been great. Good luck with your cloud coverage, and I hope your observations come out fantastic. And thank you again so much for spending the start of our live stream with us.
Thank you. Yeah, thanks for having us.
Of course.
Okay.
Bye.
Bye. Thank you guys so much. So we are going to take a short break while we get our next speakers in the room and ready to go. But feel free to check out our website in the meantime to look at our current forecast, and we will bring those back up when we come back from our break. Hello and welcome back to Coronacast 2024. For those of you who weren't here at the start of our stream, my name is Catherine Wilbanks, and I am part of a student-led group between the University of Michigan, Climate and Space Sciences program, and the University of Texas at Arlington's Physics Department. We have been here for the past week modeling the sun's corona, or the outer atmosphere of the sun, in hopes that our model proves to do well up against observations that we'll see later today during the total solar eclipse. We're actually going to go around the room real quick, and everyone's going to say hi, and we're going to show off our latest forecast.
Hi. So I'm a first-year PhD student from the University of Michigan doing solar physics. So I'm mainly doing the numerical simulations in the space project. I'm doing the simulation of the solar corona and generate the output for our prediction of the eclipse.
Hi, I'm Weihao Liu, and I'm a second-year PhD student at the University of Michigan. I'm doing the solar and heliospheric physics in this project. I'm also doing the simulations.
Hi, I'm Jim Manchester, research professor, University of Michigan. I work primarily coronal physics, coronal mass ejections, simulating the corona. In this project, I help with advising the students.
Hello, I'm Amy Rewald. I'm a second-year PhD student at University of Michigan. I primarily do magnetosphere physics, but in this project I'm helping with graphics and tying up any loose ends that we may need tied up.
And at this point, we're going to throw it over to Shan Yu, excuse me so much, I'm very sorry, who's going to tell us about what our current prediction looks like. So right now we have white light images up.
So what we're seeing in this figure is actually our prediction for the white light images. And white light images is basically what we're going to see during the eclipse by our naked eyes. And the white light images are basically the scatter white light signals of the solar corona, and they can represent the structures of the sun, like some streamers stretching out to the heliospheric space and some coronal holes, and we're going to learn a lot from these images. And these images have the Dallas, Texas, north-up view, so it's comparable to the real observation.
Okay, and then we're going to go to the polarized brightness.
Okay, so polarized brightness is basically another signal associated with the white light. It's actually a subtraction of two signals in two directions. And it has more contrast in this image, and we can more clearly see those structures.
And then the emission lines.
And so these beautiful emission line images are combinations of the spectral line images that we synthesize from our models. So in solar corona, the temperature is extremely high, more than 1 million Kelvin, and the ions are fully ionized, and they are producing the spectral emissions in some specific wavelengths. And what we're seeing here is combinations of the spectral lines that have different sensitivities to different regions. So we're going to see different colors in different places in the sun. Like in those regions with the red, the temperature is very high, and those blue and green regions, the temperature is a little bit lower.
And then the wonderful magnetic field visualization.
Thank you. So these images are showing now how the magnetic field looks like in our models. It's actually a 3D rendering of a physical variable called the scratching factor of our magnetic field, and it presents the 3D structure in our 2D images. And we can see a lot of structures at the coronal lobes, like the streamers and magnetic field stretching out further in the heliospheric space, and how they connect as some open and closed magnetic field lines.
And then finally, the extreme ultraviolet.
So extreme ultraviolet is very important observable that we'll learn about the solar corona. So they're not seen by the naked eyes, but they can be seen by some satellites and telescopes in this space. And so the extreme ultraviolet are actually produced by those plasma with extremely high temperatures, and they're really sensitive to the temperature and density distribution in the solar corona, and we learn a lot about the solar corona structures from these images.
Okay, yeah. Thank you guys very much for that quick update. I think we're ready to pass it over to Catherine.
Yeah, thank you for the update on our latest forecast. And now, with us to talk about the sun and the observations that they're making of the sun, we have a group called Iron Sun who are out in Arkansas today. Hello.
Hello.
How are you today?
Well, we're good. We were supposed to be in Texas, but we ended up in the Ring family home, who graciously hosted us in their courtyard to do eclipse observations for an entire family and village here. So we're running we're hoping to run our experiments. The weather seems roughly good. We'll see what happens in the next 2 hours, but there's great hope that we will be able to do something. So we're here and we're going to the end trying to get our observation.
Great. So why don't you actually tell me a little bit about your group and what you are hoping to observe?
So I'm a postdoctoral researcher at the National Solar Observatory, and I'm in a mixed group of researchers and students from the National Solar Observatory and the High Altitude Observatory. And we're running 2 field experiments and 1 outreach program. One of the field experiment is Iron Sun, which is led by me, and the other experiment is called Cheese, which is led by Momo Molnar. And these 2 experiments aim to image and take spectrographic snapshots of the corona during the totality phase. The Iron Sun will do imaging in iron lines to get the highly structured and high temperature maps of the corona. And the Cheese experiment will try to find the elusive helium line that is prognosed to form or not in the corona.
Fantastic. We'll actually loop back to those in a little bit, but I kind of want to start out by asking a pretty broad question, but what exactly is our sun?
Our sun is a star. It's a pretty mundane one, I would say. There's enough of them in the sky. The only difference is that's really it's close enough, so it's not just a point source, and it also keeps us alive. But those are details.
What kind
so?
Of... No, yeah. Go ahead. Well, the follow-up question that I had was, what's kind of the structure that makes up the sun? It's a normal star, but what does that exactly mean?
That means it's pretty average in most of its parameters if you put it on a diagram and compare it to other stars. So it's not too hot, not too cold, not too big, not too small, not too red, not too blue, perfectly yellow.
The perfect sun.
Yes.
So what makes up our sun and other stars?
So most stars and our sun are made mostly of hydrogen and a significant proportion of helium, and then there's trace elements, which are important for our scientific understanding of the sun and stars, but they're not really, they don't make a big proportion of the mass of stars.
So,
which these are irons and all sorts of other elements from the periodic table.
So there's a lot of solar scientists like ourselves, like yourself, who have gone and traveled a large distance to be in the path of totality. Why exactly do solar scientists like us care so much about total solar eclipses?
Eclipses are cool. That's it. And most people don't really manage to see many during their lifetime. They're rare. They change locations often. You might get a couple of them in a short periods of years, but then you might get 20 years of nothing. And it's a hard thing. Although it's quite it happens quite often, eclipse phenomena are quite rare to observe. And on top of that, not all eclipses are total. And because of that, total eclipses are even more rare to see. So we went all the way from Colorado to Texas down. We decided that won't be a good place due to the weather, and then we came back up to Arkansas. It's most of our team actually, and we are 7 solar physicists here, and there are a couple of us who have never seen a solar eclipse. Myself has only seen an eclipse in 1999 when I was a small child. So I don't remember much. This is almost my first, I would say.
Yeah, this is my
And
first total solar eclipse as well. So you talked about how y'all are imaging the sun in very specific ways. How do you guys do that? What's the difference between a regular telescope and some of the instrumentation that you guys are using today?
so we will use the power of the total solar eclipse. That it blocks the main radiation from the light, which overwhelms everything else. By doing that, we are able to directly observe the corona with a high degree of accuracy, I would call it, which is usually better than what eclipse faking instrument would do from the ground. And what we do, the corona is, as you know, very hot compared to the surface of the sun. And in order to see these lines, we need the eclipse, and we need specialized instrumentation and specialized observing setups to do that. So you usually build either a spectrograph, which decomposes the light into quantifiable sources of light based on its energy, or you use filter images to block all the light except the specific narrow light that you want to see, which again cannot be done without outside of the totality phase of an eclipse.
So how many instruments do you guys have set up there in Arkansas?
We have two science grade instruments, the Iron Sun and Cheese. And then we have a couple of smaller imaging telescopes, and we're going to do calcium observations of the chromosphere in the partial phase, or even hydrogen observations based on what will be better based on how cloudy it is. But our main 2 experiments are aimed specifically to study the corona during those 4 minutes of totality. And we spent a couple of months building them. And now we're hoping for clear skies to actually use them.
We are hoping for clear skies as well. So some of these images that you guys are looking for with the iron bands and the helium, what exactly is that going to tell us about our sun? What are we hoping to learn?
We know a lot of stuff about the sun, but we also don't know a great number of things. And my experiment, the Iron Sun, is attempting to capture the 2 iron emission lines that form in the infrared, and then test how accurate our theoretical predictions of how these lines form and develop are compared to reality. And as a side note, we're also going to get a density map of the corona at temperatures around 1 million degrees. And to talk about cheese, I might actually invite my colleague here, Momo.
Absolutely, bring him on. The more the merrier.
Who is the PI of that instrument, and he can tell you a couple of words about it. Come on.
Oh, hello.
Hello.
Oh, hi. Oh, sorry. Please go ahead.
No. We're excited to hear about your experiment cheese and what you're expecting to see about it and learn more about our sun with it.
Yeah, we are fielding today an experiment that is going to look at the presence of helium, and in particular neutral helium, in the solar corona. This is interesting because this work has been based on previous measurements, which have been highly controversial, and they haven't been repeated in about 20 years. So we are trying to repeat those measurements, and they're very important because if we can detect neutral helium, that would allow us to make significantly better space weather forecasts. As there's weather on the Earth, there's weather in space, and we want to make better space weather forecasts. So today we're trying to detect if neutral helium is present in the solar corona, and if so, that would allow us to make better forecasts for the space weather.
That sounds great. And I've got to ask, where did the names come from?
Well, in my case, I had the letters that I had to make an acronym, because usually we name instruments as acronyms based on the first letters describing the instrument. So in my case, I was studying the corona and I was looking for helium. And the type of instrument I'm using is called a spectrograph. So you see that I have the C, H, E, and S together. So I was like, oh, I can add an experiment at the end and make it cheese. So that sounds better. So what my experiment name stands for is the Coronal Helium Emission Spectrographic Experiment.
Perfect. And what about Iron Sun? I mean, I think that one's a little bit more straightforward, but
Not really. I'm not as cool as Momo, but actually I'm from Romania, and the first three letter, FES, means a beanie hat in Romanian.
no.
So I said, well, I'm studying iron, I'm studying the sun, and we can put a little beanie hat to make an eclipse of the sun. So that's Fesan.
That sounds so cute. Thank you guys so much. But there are a couple of other questions I wanted to ask. So, what are some of the important dynamics behind the total solar eclipse that we'll be able to see today?
Okay. Momo's called back to his setup.
Yes, of course. We understand that we're getting close to totality here, so we really appreciate the time.
Yeah.
But yeah, what are some of those important dynamics?
So to my knowledge, there was a small CME erupting a couple of hours ago from the sun, and it will be interesting to see if anyone can capture it.
Oh yeah, absolutely. That's actually your breaking news for us. We all just got very excited in the room.
Yeah, we'll see what happens. I don't go too far away from the limb, so the CME might have passed by now.
Mhm.
I'm not sure if I'll be able to catch it, but other people who have wider field of views might have a good chance of getting it. So that's one dynamical event that just happened. And there are two sunspots which we don't care about because we're blocking them. But other than that, I'm not aware of any major eruptive event that's going on. But there might be some interesting dynamics in the so-called coronal streamers, which are very variable sources of movement in the corona, and they might show interesting results which might help space weather applications, and how do we accelerate particles into and answer questions like how do we accelerate particles into the interplanetary space. But usually to do this, we usually tie multiple observatories and instruments together. So for example, the two of us are taking observations from the ground.
Mm-hmm.
There's Jenna Samra, who will take observations from a plane in similar lines. But very importantly, both Solar Orbiter and Parker will have something for us. So in the last years, and it's becoming more and more important that we collate data sources and analyze them together as a source to find new and groundbreaking information about how the sun behaves.
Yeah, absolutely. I think it's always kind of a shock to people when I talk to them about our sun and how much we don't know about our sun. But one of the things that we do know is that it's on a typical solar cycle of with solar max and solar min. As we're going into solar maximum, what are you expecting that to change for observations today?
Well, this is a tricky question. So technically, we're right in the middle of the solar maximum.
Mm-hmm.
But last week, for example, there was no visible sunspot on the solar disk, which made aligning the instrument and calibrating very painful.
Oh no!
So usually solar maximum phases of cycles have a big dip in the middle.
Mm-hmm.
And if we are to believe, and if we are to make a prognosis based on the previous solar cycles that we observed, we're right in that middle part of the maximum phase where the solar activity decreases by a lot. Then there will be a second phase of the maximum, and then the whole activity will slightly wind down towards the minimum.
Yes, and
So I was actually hoping to have a proper maximum, which 3 weeks ago it seemed like it. We had a lot of eruptions, we had a lot of sunspots, and then last week was nothing.
yeah, it's been pretty quiet this past week, but we are still hoping that
Yep.
we see some unique structure in the corona in observations,
Oh,
especially with those streamers and solar prominences that we've been talking about today. So,
yes, even if we didn't see even if you don't see visible sunspots, there are a couple of them on the far side of the sun, which we don't routinely observe and or close to the limb. So you will see a lot of structures that will probably will be very close to the model, the predictions by OSA.
hopefully, we're really hoping so. We're excited to validate our models with observations later today. But some of these structures that we've been talking about, we've kind of been discussing that we'll be able to see them during totality. But what causes them in our sun?
This is an opinion-based answer, and my crux is the magnetic field. Magnetic field is the primordial factor that causes that shapes the activity of the sun, its dynamics, and its and the extended coronal structures. So that's a regime where plasma doesn't have that much influence, but the magnetic fields that govern the very few particles that are there, they become critically important. And those structures normally map magnetic fields that we see in the corona. So I'll be very eager to test what we observe with predicted magnetic fields and see how closely they match, what discrepancies exist, and so on.
Yeah, we are too. We're hoping that groups like yourselves are able to send us in some observations so that way we can compare them live on stream later today. But I guess I kind of also wanted to ask you about your own personal experiences with total solar eclipses. Is this the only eclipse that you've ever seen, partial, annular, total? And if it is your first one, what are you excited to see?
It's my technically second total, but I don't remember the first, so it doesn't count. I've seen a couple of partials, but nothing compares to totality. So, for example, I organized an expedition last year for the annular solar eclipse, and we did see the annular solar eclipse at a national park site in Utah, but they're two very different experiences. So you're either on the totality path on a total solar eclipse or not. In the annular phase, even if the disk, the moon completely passes through the disk, the orbital distances and the numbers are not right, so that you still get too much sunlight, so you don't get the darkening sky, you don't see the corona, and you don't see the Baily's beads or anything that's really the outstanding part of an eclipse, the profound part, which we are hoping to see today, hopefully.
Yes, hopefully. So
we have about 3 members who haven't seen, who don't even vaguely remember a solar eclipse. So I'm hoping that they will be able to see the totality today.
Yeah, most of our team has also not seen a total solar eclipse, so we are also hoping. But speaking of hoping, how are things looking for you guys out there in Arkansas? Can you see the moon is already starting to occlude part of the solar disk? Are you guys looking at a lot of cloud coverage or clear skies right now?
We are about 20 minutes from the start of the partial, so not yet.
Okay.
We might be able to point a small instrument and observe the moon, but it's kind of dangerous, and we have a lot of public here, so most probably we're not gonna do it, because any small movement might steer it towards the sun, and that's something that people should not do, because we will not be able to observe the moon with solar filters. But no, 20 more minutes and we'll start seeing the partial. We will see the eclipse visually. The sky is good enough. Our only question is whether we'll be able to actually get science grade data out of it, because there are a few high atmosphere scattered clouds in the very highest layers of the atmosphere, and they might make the observations difficult to acquire.
Of course. I think we're looking at very similar cloud coverage here, which I think is why a lot of scientists like yourself have decided to place their bets on Arkansas instead of Texas this year.
Well, we placed our bets on Texas, then we changed our bets.
Well, I also hear that Arkansas will be getting a total solar eclipse the next time we can see one in the continental US, so they might just be extra lucky.
Maybe. I know the next one is 2044 in continental US, but I have not checked the path, to be honest.
Oh, that's quite all right. So a couple of other questions about our sun. We've kind of talked briefly about solar flares and CMEs. What exactly is some of the mechanisms that are driving these phenomena?
So you can phrase it as energy gets built up by tensions in the plasma, by magnetic tensions, by different forces. At some point, those energy buildups that the sun creates through its rotation will start breaking. That will lead to a local cataclysmic event, which we usually associate with flares. And then we associate flares with eruptions like coronal mass ejections. So it's a gradual buildup of energy, and then a very fast and extremely impulsive energy release. And one of the main questions that come up today to scientists is whether we can predict the occurrences of these events. And that's why we need more modeling groups, and we need people to model the whole sun in order to further understand these phenomena. We also need observers to confront and validate those models. So it's always collaborative.
Oh, yes, absolutely. We've been collaborating with people all across the field these last couple months, so that way we can see observations, working with other people who model the sun to see what differs in their models compared to ours. And we've actually been running our models with a lot of different inputs and parameters to see which configurations will hopefully produce the best models. So we talked a little bit about the CMEs and solar flares. So after they erupt from the sun's surface, they begin to travel to Earth. What's some of the space weather effects that we see from this?
Space weather is it's dangerous to some extent. We have historical accounts from cataclysmic space weather events, but as a modern civilization, we never really experienced a cataclysmic one. So that energy that gets released by the sun in an impulsive way might be directed towards the Earth. If it's directed towards the Earth, there's some very complex things that happen in the interplanetary space, and based on that sum of complex interactions, it will hit the Earth in a certain way that might make it more or less dangerous. And we do not have a modern equivalent for a cataclysmic space weather event. But based on all of the historic accounts, we should prepare for them. At some point, one will come. And these events might be very dangerous to our communications grid and satellite networks, because the energy flux that's coming per second into spacecraft and energy grids increases so much that you might overwhelm them. And from the ground, the most common space weather phenomena are auroras that usually form in the polar regions, both Australian and Boreal one. But sometimes those auroras come at lower and lower latitudes. One of those historical events I was mentioning earlier mentioned auroras at tropical latitudes, which if that would happen would be quite dangerous for our technology.
Yes, and quite unusual. So as we are starting to approach the total solar eclipse, what are some of the phenomena that you're most excited to see, barring cloud coverage? are you just excited to see if your instruments are all working?
Instruments are pieces of metal and software. We are interested to see and observe the corona. You put work in the instruments, and then hopefully everything aligns well and nothing breaks. You know the idiom that anything can break will break, and we've been experienced that for the last couple of days. But hopefully nothing more will break, and we'll be able to take our observations and learn something new and exciting about the corona.
Hopefully. Is there anything that you're excited to see besides the corona? Any phenomena?
I'm very interested to see if I can find any signs of the gravity waves that form in the Earth's atmosphere because of the rapid decrease in temperature due to the eclipse. And there are some tell signs that appear that are anecdotal to a sense, and they appear to some people in some places, but not everywhere. So I will be looking, keeping an eye out for these atmospheric gravity waves.
How do you keep an eye out for such things?
You should see a rapid forming, linear pattern in the atmosphere, similar to clouds, but they're not really clouds. It's some form of temporary condensation that will disappear immediately after the totality ends. So you should see some striations to the how does it work? Pretty much you should see them towards all sides of the eclipse. It's not really circular because there's also some geometry that changes it. But again, it's very anecdotal. It's rarely reported, but it sparked my curiosity.
Yeah, absolutely. I think we will also be on the lookout for it too during totality. But I wanted
just to mention, scientists do observe them with specialized equipment. I'm just interested in seeing if you can actually see them with the naked eye.
Yes, absolutely. That would be pretty exciting if we can.
So they're not phantom phenomena that might or might not exist. They exist. They're well documented, and you can observe them with specialized atmospheric instrumentation.
So what now?
All right. Well, is there anywhere people can find y'all's research and more information about your observations that you're going to be making later today?
So we're gonna try to do some media coverage through HAO's and NSO's channels, and I will post pictures and whatever I can get to my LinkedIn of the observations that we're taking are quite complex, and we don't know if we'll be able to process them on the spot or if we need to go back home before we can have a nice image out. So in my case, in order to achieve the required resolution for and spatial coverage for my experiment, I had to mosaic the sun in 4 different sectors, and I'm moving my telescope to the 4 different sectors. And then I'm gonna have to restitch and reassemble the full image of the solar disk.
All right. Well, good luck with that. Thank you again so much for spending time with us so close to the total solar eclipse. You had some great insights about our sun and about how we observe it during total solar eclipses. So I want to thank you one last time. And hopefully we all get to see some clear skies.
Yes. I'll get back to my instrument. Thank you for having me.
Of course. Thank you so much. So we are going to go on
Have a great day.
You too. We're going to go on another quick break real quick. And then when we come back, we will actually be talking to some of the scientists that have been in the room with us today. We'll be talking to Chip and Dan about how we actually model the sun and how we've come to our forecast that we're presenting to you today. So join us back here in a few minutes.
Okay, welcome back to the Coronacast live stream. I'm Dan Welling. I'm an assistant professor at the University of Michigan. And I'm going to take over and give Catherine a break for a while because she's been working real hard. I have with me research professor Chip Manchester from the University of Michigan. And we're going to interview Chip in just a moment. Chip, you and I go way back, like car seats and spinal cords.
Yeah, that's right. Since since the time you were first a student at the University of Michigan. I mean, I came there, joined the faculty in 2000.
Oh, wow, yeah. So just a few years later.
Yeah.
Yeah, you got introduced to that guy who keeps hanging around the department for some reason.
That's right.
So, as a reminder, the Coronacast project, this is a student-led project where not only are we doing a lot of outreach this week and talking about the eclipse on this live stream, but also in person in schools around the Arlington, Texas area. But we're also, I'm going to point it over to some of our modeling team, give us a wave real quick. A number of students who have been running computer simulations, which I'll throw some of the results up on screen and let them cycle through, of what the solar structure is going to look like in, what's our countdown at? Just a little more than an hour now. This is really challenging to do, to predict what the corona looks like at any given time. And trying to do it for an eclipse is this moment where you're putting your money where your mouth is in terms of the physics, the computer modeling, and we really hope that when, first of all, there's no clouds in an hour here in Arlington, Texas. But then once the clouds go away, we can look up and see exactly what the model said we'll see in terms of the corona. And speaking about the weather, what we're going to do now is we're going to bring up our man on the street. This is Hudson Gregory. And Hudson, I'm going to unmute you. How noisy is it out there on the campus of the University of Texas, Arlington?
Yes, we are outside of the Science Hall of UTA right now. We've got a pretty big crowd around here. There are a lot of students out here to try to see the eclipse. It is fairly cloudy out, as you can probably see. It is the sun keeps hiding behind clouds, but I believe it's out. Let's hope it stays like that when the eclipse is actually happening.
Oh, thanks a lot for that. So is it right now? We've been locked up in this room working for a long time. Could you tell us, is it a mix of high up clouds and big puffy clouds? Is it just a lot of big puffy clouds? What is it? What are you seeing out there?
There's quite a few big puffy clouds. There's a lot of opening area, but there's a lot of just giant clouds that will cover up the sun for a while and then go away. So let's hope that when the eclipse happens that we have more of a just instead of clouds covering it, we just see the eclipse directly and that there's nothing in the way of it.
Very good. Yeah. And is it not overcast, but just kind of scattered cloudiness, eh?
Yeah. It's not like foggy, cloudy, no.
Yeah. And is it, are the clouds moving fast? I ask because we have under 4 minutes of totality here in Arlington. So if the clouds are moving fast, we might even be able to, we might be able to see the totality even for a moment, but if they're moving slow, we could be really unlucky.
No, unfortunately, they are moving quite slowly. They are moving, just not enough for it to really work out that we're guaranteed to see it.
Yeah. Could you do me one last favor? Could you give us one last view around campus there? Earlier, just a minute ago, while we were in break, I heard music playing, theme to the eclipse. I think I heard Moonshadow playing through the window.
Yeah, they are
cool.
They are playing music out here. It's just gotten much quieter, I think. They're in commercial break right now.
Well, thank you very much. I really appreciate you running around out there and keeping us updated.
You're welcome. Thank you for having me.
We'll talk to you in a bit. Okay, so I'm going to turn it back over. We're going to talk to Chip Manchester for a while. And Chip, I know you as one of the big solar physicists in our group at the University of Michigan, but could you tell everybody out there what it is you do and a little bit about your specialty?
Primarily I work within our group simulating the solar corona, and primarily I focus on eruptive events. coronal mass ejection, simulating those directly, also looking at some fundamental theory about how the energy builds up to power these events. And I've also worked with forecasting models with machine learning, basically, where I'm helping, collaborating with machine learning experts on providing the data and how to interpret these models.
Very cool. And getting to the point where you are now, you've been at University of Michigan for a while, but can you tell us where you were before that, where you got your degree and how you got where you are?
Oh, sure. I got my PhD at the University of Illinois and did the research at NCAR in Boulder, High Altitude Observatory.
Very cool, very cool. So at this point, I'm going to go ahead and pull up, you've got some slides for us to talk about the physics of the sun. So if you just want to walk through these, and if there's any questions I have or any questions we get in chat, I'll be happy to ask you and interrupt as rudely as possible. But
sure.
Yeah.
I want to go through these slides just to give kind of definitely some context for.
Oop, I'm sorry, I covered you up for a second. Go ahead.
For the total solar eclipse, why it's important to us. See if we're seeing the image right now.
Yeah.
We're looking at a white light image of the sun. And we see essentially very little structure. It's basically a uniform ball of what looks like uniform intensity white light. And basically the only exception, the only structure we really see are sunspots. And in this case, the magnetic field is very intense in these sunspots, and it's strong enough that it inhibits convection, which allows the surface to cool off more than the surrounding photosphere. So this whole thing is like a boiling cauldron of hot plasma. As that rises to the surface, it cools off, and it begins to, of course, emit very strongly in radiation as it approaches the surface. It becomes optically thin, that light and heat escape, and it cools off, and then it sinks back down. Well, the magnetic field is concentrated and begins to inhibit that convective motions, so at the surface it can actually cool off but not return quite as quickly to the deeper part of the sun. And so it actually cools off by more than 1,000 degrees centigrade compared to the surrounding surface, and so it just appears dark because it is simply much cooler. Now the things really get interesting when this magnetic field expands into the corona, and the opposite happens. First of all, the magnetic field expands to fill all of space. So at the photosphere, all we see are really small, intense flux tubes, or active region fairly large, but still in terms of the total scale of the sun, are rather limited in scale. But when this magnetic field goes out of the photosphere, it is no longer confined by the pressure of the atmosphere. The pressure falls off much more rapidly than the magnetic field strength, and the magnetic field fills all of space surrounding the sun, and it completely structures the outer atmosphere that we call the corona. And this is why we call it the corona. This is a combination image made by Shadi Habel and Druckmuller showing the image. This is an image of the sun during the total solar eclipse, in which it's possible to view the outer corona, this outer atmosphere of the corona, in the visible light in specific spectral bands. And so what we're seeing is light in the visible spectrum coming from the corona, and it's dominated by a few colors. So you see the chromospheric color. This is a deep red, known as the H alpha band, which is coming from the lower atmosphere. And then higher up, you're seeing emissions in the green line and other visible lines. And so you get this combination of colors coming from specific lines in the visible spectrum. And it's seen a long ways out in the solar corona. So very, very pretty, absolutely gorgeous, stunning image showing, again, the structure of the magnetic field. So you see a lot of linear structures. You see loops. You see these lines radiating out from the sun. And basically, this delineates the magnetic field structure. So wherever you see a line, it's pretty safe to assume that there's a magnetic field essentially running nearly parallel to these structures. And so you see open magnetic regions that are just expanding out in space, and you see loops, which are basically colored green and red. So there's denser plasma at a different temperature, typically higher temperature on these closed loops, and it emits more strongly in these spectral lines.
So before we move to the next slide, I have to ask, I think we've both seen a total solar eclipse,
Yeah.
but for our viewers, how much of this that we see on the screen right now is going to be visible?
Actually, a lot, a great deal of what that's a really spectacular part of it. The human eye is extremely sensitive and has an enormous dynamic range, much more than typically normal optical instruments. And so you can actually see the corona deep down, low, very close to the the base here where it's very, very bright and much brighter than the outer part, which is still visible to your eyes. You can see over a wide range of brightness levels. So you can see these outer loops forming at this distance and even further out with the naked eye. And then you're going to be able to see red features, these chromospheric features, filaments type things near the base of the corona. The green isn't going to stand out quite like that. It's going to be mixed in with some other colors. So you're not going to see just but you might see overtones of green, different colors in various areas. But it's going to be more of a mixture. It's going to look kind of grayish white, but you'll definitely see that bright red at the base of the corona. It's called a chromosphere, specifically because of that color.
Very cool. Very cool. So, yeah, this is a spaghetti bowl here.
Yeah, so we're going to jump into what the structure of the corona looks like in our numerical simulations, where we're trying to pull out what was just seen. So if I can actually go back a couple of slides and we can show what it looks like here, okay? And so this is what we have at the base of our coronal model. We have a magnetic field that is specified from observations and covers the entire surface of the sun in our numerical model. And then jumping back to the simulation, that's what we're showing here at the inner surface here. This is the photosphere, the base of the corona, basically near the transition region. And what is being colored here in that grayscale is the magnetic field. And you see these black and white regions, which correspond basically to sunspots, active regions, and strong polarities, strong magnetic fields in the sun. And when you look at them, and we're looking specifically now at the radial component of the magnetic field, you see that it reverses direction. So these sunspots come in pairs, which are of opposite sign, and there's magnetic field connecting a positive to a negative loop, to a negative polarity, forming a loop system, and that loops eventually begin to open up in space. So that's what we have to fill our model, an observed radial magnetic field, again, and these structures correspond to active regions in the sunspots closer to the equator. Now, what's being shown on the surface, on the cut plane in this bright dynamic color, is the solar wind speed on a cut plane. And so you can begin to see just incredibly how structured this is, the solar wind speed. So this corona begins to expand and accelerates out into interplanetary space. And this is showing that velocity on a scale from 0 to blue to 50 kilometers per second, going up into that white color. And this is just the beginning of the acceleration. It continues to accelerate up to several hundred kilometers per second. The right, now what we're showing is the magnetic field line in full 3 dimensions. And so these, again, now you can begin to see these field lines connecting opposite polarities and, again, filling all of space. And you basically, now you can see how the structure of the magnetic field corresponds with the previous image that we saw at the total solar eclipse. This magnetic field, again, is filling space and structuring the corona and forming these loops. And you begin to see the open field lines more near the poles where that solar wind is expanding out freely. And then the solar wind gets trapped in these closed magnetic loops where it becomes both denser and significantly hotter than the open field line regions.
And real quick, I think could you talk to how fast the sunspot and the magnetic structure changes as a function of time? It's certainly not static, but how quickly is it changing?
Okay, so individual active region will typically last for it basically takes about 24 hours to begin to develop a full active region from the point where magnetic fields are coming from the solar interior. They actually begin to rise with the convective motions and just pop up out of the surface. And it takes a minimum of about 24 hours to form a full active region. And then they'll be around for potentially up for weeks. Usually it would be a period of 2 to 3 solar rotations that a large active region would last, and that's roughly 2 to 3 months. So they're there for a while, and they begin to gradually diffuse away, and that magnetic field weakens and spreads out and dissipates.
Yeah. But that time evolution is one of the reasons on the Coronacast website, while we have been updating those forecasts, because even those subtle changes in the observed magnetic field can change quite a bit on the maps and the model results.
Absolutely. This is a really exciting time because, as you can see in these images, the sun has a lot of active regions. There's that black and white all over the sun, and these active regions are evolving quickly, and they completely restructure as they evolve and move. It completely restructures the coronal magnetic field. So all the loops that are being shown on the right-hand side will change, expand, move around, and the corresponding structure of dense plasma trapped in those loops will move around.
Very cool. So moving forward here, I think you're the easiest interview we're going to have today because you've brought some of the most interesting pictures. Talk us through this one.
Okay, so to begin with, the outer corona, 2 to 3 million degrees, highly ionized, radiates very strongly in the extreme ultraviolet, which cannot be seen on Earth because it's absorbed by our atmosphere. But if we put a spacecraft into orbit, in this case, this is the Solar Dynamics Observatory, launched in 2010, and we're looking at images from the AIA instrument, and we're looking at specifically 4 different spectral lines that are being combined here into one image, which are showing a range of temperatures from maybe 100,000 degrees to several million degrees. And so this part of the atmosphere is now very, very hot and radiating in the extreme ultraviolet, rather than at the photospheric temperatures which we associate with white light. This is a much higher frequency and coming from localized regions which are optically thin and very highly structured. And so we see a lot of loop structures, we see a lot of individual bright points, we see active regions are lighting up. There's 2 active regions that really stand out as being bright inside the disk of the sun. There's a lot of bright spots where there's intense localized magnetic fields. And then the real fun thing is that there's a big loop, a prominence erupting off in the upper left-hand corner. So this is not only very highly structured, a lot of intensities and temperature variation by the magnetic field, but these also erupt. And that's what's happening here. And this is a much more spectacular image of such an eruption in the 304 band of helium, which is showing the erupting filament. And so this thing is low down to the surface of the sun, it becomes activated and then pops up. And so yeah, we have absolutely enormous eruptions going on in the sun from active regions and from quiescent filaments erupting. And the next slide will show an even larger erupting loop that goes a long distance across the solar disk. It kind of wraps around the limb and comes near the top center. Yeah, absolutely enormous in scale.
So our previous interviewee, Alan from Iron Sun, he actually said that there might have been a CME being observed right now, though we haven't had a chance to confirm that. If there is one, will we be able to see it during totality?
There's a distinct possibility if it's slow moving. Absolutely, that's a possibility. We could see that, which would be really extraordinary.
Yeah.
So at the slower range, 200 kilometers per second, which is kind of a slower CME, translates into 1 solar radius per hour.
Oh, wow.
So it would be at that speed, basically, it would appear essentially stationary to us.
Yeah.
Now they can go out over 10 times that speed, and then that loop would be moving, in a matter of minutes. In 6 minutes, it would go 1 solar radius. We'd be viewing for 4 minutes. So 1 solar radius difference in that period of time would be seen.
Oh my gosh, that would be once in a generation kind of observation.
Yeah, if there's a big one that goes off on the limb, you will, and it's really fast, you will absolutely see that loop going out, which would be extraordinary.
Yeah. So I just want to remind everybody watching at home, if you have any questions for Chip, feel free to type them in chat, or anything that came up before about solar eclipses. But we can keep going here. Oops. And PowerPoint's fighting with me. That's what happens when you're doing these things live, but that's okay.
Okay, so that solar wind, as we were showing in that image, is coming out from the sun, and it continues, gets up to rapid speed pretty close to the sun, and that fills all of interplanetary space. We call that the solar wind. Typically it ranges from maybe 350 to almost over 800 kilometers per second. So quite a range in speeds, and filling all of interplanetary space and goes blowing past the Earth. And so these eruptions I just showed in extreme ultraviolet, those continue to go out. Oftentimes they go out into the solar wind at high speed, where they drive enormous blast waves that completely restructure the solar wind. Again, some of these are going out at 2,000 to 3,000 kilometers per second, which is much higher than the local sound speed. So it drives a shock wave, and it just blows everything out of its way, leaving a big cavity behind it, which you're seeing are running differences images starting at the sun on the far right side here. Both that little orange dot is the sun, and then outer rim is an extreme ultraviolet image. Then there's further out from that blue disk, and then the square disk, and then blue again, is showing Thomson scattered white light images, which are just showing basically light being scattered by free electrons. And so the brighter it is, it's simply denser material. There's a direct proportionality between brightness and density.
Oh man, so this is actually real cool. We're actually right now we're being told by the gang in the room that the CME is visible on LASCO.
Cool.
So
any chance we could pop that up?
Yeah, if you give me just a minute here, I can try to pop this up real quick. I'm actually, could you do me a huge favor and take a screenshot and put it on the Google slideshow, because then I can transition over to that. It's funny, we knew we were going to do some data model comparisons during the stream and have to juggle around some stuff during the live stream, but we're pretty excited about the opportunity for a LASCO image of CME. Yeah. I was not expecting that. Let's while they're prepping that, let's go ahead and go back to the presentation. I'll go to the next slide here and let you talk through this.
Okay, so things what was actually shown in a previous movie was this material propagates all the way from the sun and grows enormous in scale. So it's going out at about a constant angular width that could be anywhere from 50 to 90 degrees, and it just grows enormous in scale. So now we see a shock wave blasting out to interplanetary space. This is a simulation now that was made with our group at the University of Michigan, showing the structure of the magnetic field in interplanetary space going out. And this is the Earth now being impacted. So the green surface here now is the Earth's bow shock, where the solar wind impacts and basically comes to a stop relative to the Earth and has to go around the Earth. And then this is the Earth's magnetic field being perturbed. So this is an actual time-dependent simulation of the space weather event of the Earth's magnetosphere being impacted by the CME, and it's very dynamic, a lot of reconnection going on. So this is a very strong coronal mass ejection that occurred in May of 2005, going out at 1,600 kilometers per second, and drove a pretty strong space weather event. And this is an extraordinary view of the simulation, showing the scale of the structure of the magnetic field and the scale that it has now in interplanetary space, this expanding ball of spaghetti of magnetic field lines that come in behind the shock wave that we saw earlier. And now we're going to zoom in on Saturn and show its magnetosphere and bow shock, passing through the bow shock here, showing the inner magnetosphere. We see this, the magnetic field lines coming from the poles, and a beautiful representation of Saturn's rings and the system. And then we see the auroral oval, which you could speak to.
Oh, yeah.
Yeah.
Just as these interactions happen between the material coming off the solar wind and the sun's magnetic field, if that planet has a magnetic field, particles will be, electrons and protons will be excited and scattered down into the atmosphere of that planet and cause the neutral atmosphere to light up, and that's how you get the northern lights. So it's one of the things that Chip, you're one of the solar people, I'm one of the magnetosphere people. We get really excited about what the sun causes with the aurora later on.
Yeah, happy to pass off our values, solar wind values, to your magnetospheric models.
Yeah. So I want to jump back to the presentation for just a moment here, because I want to restart this movie. Could you talk to just how these simulations are done? I mean, certainly you're not pulling out a laptop here to do them, but what is the process of doing simulations, especially of this scale?
Okay, I think we jump back to a few slides,
sure,
where we're showing the simulation setup.
Yeah.
I have a slide there that shows, on the left is showing the numerical grid for the simulation. So again, what we're seeing on the gray-white sphere is basically our lower boundary, where we're specifying the magnetic field. And this is exactly the magnetic field that's going in to our numerical model. This is the data that's driving it, that is derived from observations. The magnetic field is observed from the sun as the sun rotates, and over that rotational period, with about 27 days relative to Earth, we can assemble a model, a map of the entire surface of the sun's magnetic field. And that's what we use to specify boundary conditions in our simulations. And then that's the way which it's data driven. And that allows us to actually model reality, is having that observational input. So then we have to populate that outer atmosphere. And what we're doing is we're solving transport equations, how things move around, the conservation of mass, momentum, energy, and magnetic flux in a conservative system. And so basically you're tracking the evolution, the flow of these of the system, which is why I'm showing the velocity here, because that's the rate at which things are moving, and that's the velocity of the plasma, and the magnetic field is carried along with that, in particular when it's perpendicular to that velocity.
Yeah. And so when you set up these simulations, you're basically asking NASA and National Science Foundation to use a chunk of their supercomputer. And the ones we've been doing for Coronacast were how many processors at once?
Usually around 2,000
Yeah.
or more. Yes.
That's pretty beefy.
Yeah, we'll give a call out to our supporters. That's NASA Ames Pleiades and NSF-funded machine Frontera right here in Texas.
And I also I want to thank the University of Michigan Great Lakes machine. We've been using that as well a little bit this week, with time funded by the New Zealand MBIE Solar Tsunamis Project. So real quick, we're going to break from the PowerPoint, and you're going to see me really quick fumble around with the computer. I want to show Amy and the team real quick. Guys, give me a quick wave. There. Surprise. They've been working to put the LASCO images online. So let me pull that up real quick. And where did you say that was on the PowerPoint? The first slide, of course. Oh, I have to refresh that. I apologize. There it is. Fantastic. We're obviously flying by the seat of our pants here. So please forgive me for that. Let's do it like this, and that is perfect. And make sure, so what we're gonna do, there we go. And I'm gonna go ahead and pull that up. So here's the LASCO coronagraph. Now this is just a still image. Mm-hmm. And
kind of see it in the top left quadrant.
The top left quadrant over here.
Flare coming out.
That flare coming out, so interesting. So it's not a big one if it's there. It's going to be...
Perhaps that streamer is just in the process of beginning to erupt and expand. Maybe if we had a time series, we would probably see some time evolution that might be more obvious what's happening.
So that might be something we work on a little bit on in the break here.
Yeah.
This LASCO image actually is a really useful tool to explain how important the eclipses are. The white circle at the center of this, that is the sun. That's where the sun is. And the way this image is being taken is that there's what's called an occulting disk. It's literally a disk held in front of the camera to block out the sunlight. And it has to be that big blank circle in the middle is the occulting disk to block out the light. And during the eclipse, the occulting disk for us is the moon, and we can actually see very, very close down to, very close to the photosphere. So it's really cool stuff. So we'll go back just to talking with Chip here. Really cool stuff. A lot of good solar physics in there. We got 1 minute. Oh my gosh, it's about time for us to break and go outside.
Oh, cool.
Yeah. So I don't see any. I see a couple people in chat. We have a question from Alex in chat asking if a CME has ever been observed during an eclipse.
Oh, I'm sure that they have.
Yeah.
I really can't name a specific event, but it's definitely happened.
Yeah. We had some images. Was Catherine, you were showing those earlier this week? Or, gosh, where did I see those? We've been really busy this week going around to schools and talking to a lot of different experts. And there have been some images of a CME during eclipse, but I think that's been very slow moving, slow evolving ones.
Okay.
The image we were looking at was the CME Parker detected.
Okay. So, but we're kind of crossing our fingers, one, that the clouds will part for us and we'll be able to see anything, and two, that if we do see good totality here in Arlington, Texas, or wherever our viewers are, that we might see a CME superimposed in the solar wind. So at this point, I think it's time for us. We're going to take a break.
Right.
We're going to go see an eclipse, and we'll be back. Catherine, forgive me. What time are we coming back here?
2 o'clock.
We're going to be back here
2
at
Central.
2 p.m. Central. That is 3 p.m. Eastern. One of the first things we're going to do is talk about our experience of seeing the eclipse. We hope. Our on-the-ground data might be clouds, but hopefully we're able to share some cool things. So we'll talk to the students who... guys, give me one more wave on camera, please. It's really hard to describe the work and dedication these guys have been putting in this week. Up late making sure the simulation's finished to get our corona forecast online. Really been digging in deep. Catherine's been leading the charge in terms of outreach, so it's been certainly been a privilege to work with them. And Chip, you've been kicking ass as well, trying to get a lot of stuff done.
I'm trying to help out where I can.
Yeah, it's been great. Okay, so we'll cut to the to break now. We'll be back 3 p.m. Eastern, 2 p.m. Central, hopefully with good news. So thank you guys for joining, and we'll see you later. Unmute you. I'm so
Oh.
sorry.
It's not a live stream if there's not technical problems. Welcome back to Coronacast 2024. We've just come back inside from watching the total solar eclipse here in Arlington, Texas, and the room is kind of abuzz with energy. We had a very close call with some cloud coverage, but we're able to see everything at the last minute. So I think let's go around the room and everybody's impressions from their first total solar eclipse.
It's breathtaking, amazing, remarkable.
Anybody not speaking in cliches?
It was very cool.
Yeah, we got
That's the one I missed.
our man on the street here. I'll just try to turn this camera without knocking 10 things over here. Our man in the street is now the boy in the building. Say hi to Hudson. What do you think, Hudson?
It was very, very cool. There were a lot of like neat things about it. We got to see, what was it called that was like going across the sidewalk?
Shadow bands.
Shadow bands.
Yeah.
At like once it was over, it was a really neat experience.
I didn't get a chance to see the shadow bands the first time. So for me, that was, in 2017 I didn't see them. I gotta move this camera around, sorry for the noise.
We didn't get to see them as we were approaching totality because we had very, very close call with clouds. But as totality began to edge away, we were able to see shadow bands across all the sidewalks out in the quad here at UTA. Which, for those of you who don't know, shadow bands occur just before and just after totality. It's when there's a small enough sliver of light coming down from the sun at that point that the light waves actually get interference from our atmosphere. And so when you're looking at large white surfaces, you can actually see the lines of light actually dancing around.
Now that I saw it in person, I actually know how to describe it.
Yeah.
Which is, like the cliche, when you looking at a desert in a movie or something and you see the shimmering from the heat. It's that, but projected as a shadow, wiggling on the ground.
Surface, yeah.
Yeah.
So should we cut back to the other side of the room?
Absolutely.
John Yu Weihao, what do you guys think?
Incredible. The best image I can see from the sky, the sun. Yeah.
I just can't stop screaming. I want to cry. I didn't expect it to be so clear. I thought it to be rigorous or just can't see the edge very clearly, but it just incredible. I see everything I don't expect. I'd expect.
It was good. Chip?
It was very dramatic. I mean, we had the cloud pass directly in front of the sun, basically 2 minutes before totality, threatening to ruin the entire experience. We thought this can't really happen. It's just going to be drama, and that's exactly what it was.
There were lots of screams of "Oh no" and booing at the clouds.
Yeah.
Mostly from Dan.
Yeah, mainly from Dan.
Yeah.
Oh my gosh. Oh my gosh, I was gonna say something I completely forgot. You could see this. So compared to 2017, this was like definitely solar max in the number of streamers I could see at the same time, and you could see there was that one prominence in the like the southeast corner. You could see
so clearly.
Yeah.
So just to recap that again, the sun moves on an 11-year cycle between solar max and solar minimum. When at max, the magnetic field is being rearranged and we see a lot more activity coming from the sun, which we were able to see with most of the sun being blocked out. And when we're looking straight up at the corona, you can see a lot of that magnetic field coming out from the sides. And we were hoping to see, there was a CME not too long ago, we were hoping to see some of the structure left over from that, but I don't think we saw that quite so clearly.
Yeah. Let me see. Oh, I'm trying to find I lost the presentation. I was going to flip through some slides. Yeah,
I think a lot of us are kind of speechless after that. I mean, we've been working so hard for the last couple months on just trying to get our models right that actually seeing totality has left us speechless. So if you can get some of those images up, these are just preliminary images that we took while we were out there. We are still awaiting images from a lot of the observations that we've been in observations and all sorts of people that we've been in contact with the past couple months. However, with the cloud coverage over most of the United States, some of them we might not be hearing back from.
This is so we just on screen now. Amy, where'd you grab these ones from? These are yours?
These are mine that I
Holy
took with my
smokes.
phone camera. So
shout out to Google Pixels.
Yeah, please send me a new phone. This is not sponsored by Google Pixel.
By the way, can we
not?
Before we get too deep in this, can we just take a second and talk about some of the things the DJ outside said?
There was a moment when the clouds were covering and the DJ did say you can still take a look up there without your eclipse glasses, and we were all like, no!
It was like 10 minutes from totality, yeah. And the poor, I mean, they're doing their best. They did a good job.
Yeah, they were
emceeing.
doing great, but that was wrong.
Yeah.
However, his co-host pretty much immediately did correct him, which was good.
That was pretty fun.
DJ, the enemy.
So I guess what we should do is, do we have slides? I'm gonna flip through. We gotta put our forecast next to these, right? Mm-hmm. So I'm gonna just flip back to myself while I hurry up and hack this together. If anybody has anything else they want to say.
Well, I'm kind of curious, Chip, you've seen totality before. How did this differ from the last time you saw it?
Well, it was solar minimum when I saw it 2017, so the streamers were a lot more obvious. They're just much larger at solar minimum, so that part was much more distinct in that sense.
Mm-hmm. Can you walk through exactly what solar streamers are?
Oh, right. So those are basically the bright projections coming out from the sun. It's almost what you sort of have a canonical image of the sun, you know, that has these little daggers coming out, right? And they can come to a point. And so those really do exist and are seen in an eclipse. And so that is the fundamental structure, basically. You have open spaces, and then you have streamers, which are brighter, and then they come to a cusp, usually about 2 or 3 solar radii out. But they extend much further at solar minimum than they do at solar maximum. Solar maximum, like kind of the structures we were seeing, were terminating pretty close to the sun. Mm-hmm. So a little harder to see.
And I'm trying to watch chat and do a couple of things at once, but who was this? Shanyu or Wei Hao made this slide? The one that's currently up.
I made this slide. I just copied Amy's image here and.
Where are your images?
There, pardon?
Where are your images, Dan?
Oh, I need to upload them. Yeah.
Yeah, that'd be great because you can see a lot more structure in yours.
Yeah.
Well, why Dan works with technology.
I'm gonna scoot over and handle that. Yeah.
Johnny, why didn't you walk us through the comparison between the image on the right and the image on the left?
So in the laptop, we can see a very large streamer straight out to the laptop direction, and we can probably see a little bit of that clue in the image that was taken by Amy. Then in the laptop, we can see something stretching out. It's not very obvious, but actually it is. And the left bottom, there's also another streamer. It's also stretching out, and it's a little bit larger, but unclear, but we can still see it. And right in the bottom, there's a small kind of area that is dark, and that is exactly predicted by our model in the left figure. And yeah, so in the right bottom, there's a very large region stretching out that is bright, and we also have similar kind of structures in our model. And so in the right top, it is hidden by the screen, but I believe there's also another streamer stretching out, which is predicted by our model.
And just to clarify, our model is on the left side, a picture that Amy took is on the right, and which configuration of the model was this image from?
So it's made from a depth map.
Okay. And this is just our white light images?
Yes.
So we're actually catching quite a lot of the structure already in just these simple phone photos.
Yeah.
Which is pretty incredible.
So, someone actually just already threw up the comparison already. You guys are faster than I am.
Oh, sorry.
Pardon? No, that's fantastic. Let me.
I saw you editing it.
Yeah, no, that's great.
Just
I have to.
make the image a little larger and then it
Yeah.
should be ready
Give me
to view.
2 seconds while I
This is definitely
refresh
the
the
more
proposal.
on the fly part of the stream.
Yeah.
You know, we're doing pretty good
Yeah.
for being so on the fly.
We're kind of coming down from that totality high.
Yeah, it was.
Oh no.
It was definitely a dramatic event.
It was.
I think one of the things too is just how cold, even with the cloud coverage that we were seeing just before, just how cold it got.
Yeah. Yeah, it was really cooling off.
Yeah, cold it got. The crescents and the shadows of the trees were
Mhm.
incredible. So many amazing things that you cannot see every day.
So on the screen right now, this is the, one of my images?
This is one of your images.
Thank you so
yes.
much for throwing this together. And then on the left, this is the same ADAPT.
Mm-hmm.
Yeah. So for the viewers joining us after our break, what we've been doing this past week is I'll switch over to the research team. Everybody wave. And these guys have been spending all week doing supercomputer simulations trying to forecast the visible corona that we just now saw a few minutes ago outside, which is on the screen here. We have a question in chat. What's the difference in an eclipse during a solar maximum and minimum? Does anybody want to take that?
I'm gonna just volunteer Chip for that.
Oh,
but-
okay. All right,
Yeah.
I should have done that myself. I'm just being a little lazy here. So solar maximum, a lot of active regions. I don't know if we could go to the slide. Did you bring that up from before?
From earlier? Give me 2 seconds and I'll pull
Yeah.
that up, yeah.
So we have a simulation result right now at solar maximum, which really clearly illustrates the structure of the corona, showing basically the magnetic field at the photosphere, a lot of active regions, and then we see a really complex magnetic field in the corona connected to those active regions. So
Yeah, there we go. Okay, pulling that up right now.
Okay.
And actually, I need to. I'm so sorry.
But right now, you mean in just a second?
Yeah, you know.
So there will be streamers all around the sun at solar maximum, streamers everywhere, overlapping one another, and they're going to be significantly shorter than we have at solar.
And you wanted the model results one slide?
Yeah.
Yeah,
the
I
one
just transitioned, so the stream's catching up.
Oh, okay, okay.
Yeah, it's the stream is quite behind, so yeah, I do have the model result on there now.
Okay, so the one on the left is at solar minimum, I'm assuming.
I think they're the same simulation.
Oh, just kidding. Never
Yeah.
mind. This is why I'm not a solar expert.
So at solar minimum, you're going to have basically a horizontal flat streamer belt that's in a plane aligned with the sun's equator. And so you just see two streamers on opposite sides of the sun, and they're going to be significantly larger, and they're just monolithic or dielithic, maybe the word would be. There's simply going to be two of them opposite sides of the sun. They're basically mirror images of one another, very large, extending out several solar radii.
Yeah, with the solar maximum, like Chip said, it's just crazy and all over the place. And Chip, I believe you said your impression of the actual event coming back inside was how the streamers in 2017 during solar minimum were they were more prominent because they were singular and straight out.
Yeah, much easier to see, really.
Yeah, and today it was just many different directions, and a little weaker but a little crazier.
Right, so you see kind of lower down in the corona, and it's kind of blobbier around the limb of the sun. So you see more structures, just smaller on average.
Yeah. Okay, so I'm gonna pull back up the Google slides. So we're in this room. We're like literally building results for you guys as fast as we can.
Yeah, we unfortunate timing of the total solar eclipse in this aspect is that we were one of the first people to see totality. So as it kind of spreads off across the rest of the United States up into Canada, we'll slowly start seeing more results, but being first means there's not a lot of images out yet.
Yeah. So we did this forecast with 4 different data sets as the starting points for the simulation. And do we, Shanyu, Weihao, and Chip, do you guys have any feel for which magnetogram gave us the best results so far, kind of based with our very simple images?
Well, before we even jump into which magnetogram, what specifically is the magnetogram that we're using?
I would like to say that the 8-depth magnetogram is giving us a best result that is most comparable with the observables. I mean, so we have different magnetograms and they have different physics, different processing of doing the data and prediction. And they're actually, some of them are doing well in this kind of aspect, some of them are doing well in another kind of aspect. But in terms of the white light that we see today, I'm gonna say that the 8-depth is giving the streamers that are most similar to what we see. So what we're seeing the screen is exactly, I mean the figure in the left is the model output from our model based on the 8-depth magnetogram. And this magnetogram is based on a series of ground-based observation of the solar surface magnetic field and merge them together to a single map to form the distribution of the magnetic field of this whole sun. And we use this magnetogram to use as the input data for our MHD model and run the simulation and get our model and generate the white light output as our prediction as shown here. And we compare it to the real observation and found that they're really similar.
So, I put up on the screen our forecasted white light images from the 4 different magnetogram data sets. And they're quite dramatically different. So, wow, that's pretty interesting.
And the one that we had up for comparison earlier
was the upper left hand, 8-depth map. Wow.
It'll be interesting to see how as we get more observations that are kind of a little bit more fine-tuned, how closely some of these look compared to others.
Indeed. If there's any more questions out there from the viewers, please feel free to jump in.
Yeah, we're definitely going to be in a waiting period a little bit.
Yeah. Shanyu, we should pull Shanyu in over here and let him talk through the EUV comparisons.
Yeah, absolutely.
And then Weihao, did you want to talk through the atmosphere ones?
Yeah, okay.
So give us just 2 seconds to shuffle around in here.
Shuffle some chairs.
Yeah, I don't think we need to stop the stream necessarily. But we're going to pause it for just a minute while we set up some more results to show you all.
quick reshuffling done. We're now going to be looking at some of the EUV, the extreme ultraviolet images that we've kind of modeled out ahead of the eclipse with Jean Yu here.
Hi. So if you look at the screen now, we're gonna see that there are.
Hold on.
We got the wrong one on there.
Just move it.
Yep.
Not this image.
And there you go. Sorry about that.
Okay, so here we're seeing that there are several channels of different colors in the screen, and each of them is actually the ultraviolet signals coming from the solar corona. So what is special about the extreme ultraviolet lights from the sun? So as we know that the solar corona is extremely hot, it's 1 million Kelvin in the whole atmosphere above the solar surface, and it's nearly 10,000 times hotter than what we're feeling now, our room, like 300 Kelvin. So what we're having such a hot environment. So there are a lot of ions in the solar corona, and they are fully ionized due to the such extremely high temperature. And when they are ionized, they are able to give out some lights with specific wavelengths due to their collisions with each other. And when we observe these kind of spectral lines with some telescope and satellites in the space, we can do the image to the solar atmosphere. And this is what we are seeing here. So these are basically 4 channels with 4 different wavelengths imaging of the solar corona, and they have different dependence on the temperature and the density of the solar corona. So in the first figure, it's called the 171, which means that its wavelength is 171 angstrom. And it's most sensitive to those regions has a temperature of 500,000 Kelvin. So it's actually showing a lower part of the solar corona. And as we move to the left, the sensitive temperature is going up with the second image, a sensitive temperature of 1 million Kelvin, the second one 1.5 million Kelvin, and the last one is 2 million Kelvin. So as we going from the left to the right, we can see that the region that we see is going up from the base of the solar corona and going out and stretching out. So from these kind of images, we can learn a great lot about the solar corona, especially its temperature and the density, and to validate if we're doing right in our models. And so the first row is showing what we see in the site from our MG model. And the second row is what the satellite, the SDO satellite, has just taken today. So those white points are called the active regions in the sun, and you can see the distributions of these regions are quite comparable in the 2 rows. I mean, our model and the real observations. And those dark regions are called the coronal holes, in which the coronal heating is very, very weak, but still high temperature, about 100 million Kelvin, but just weaker than surroundings. And we can see that the distributions of the coronal holes may have some discrepancies, but still comparable, especially the largest coronal hole at the right of each figure.
Yeah, if we can get, Dan, if you could highlight that coronal hole on the right.
Yeah.
And then you can really see that we're getting those
That would be
features on the left as
this
well.
one here that maps up with the observations there, right?
Yeah.
Yeah, that's a really nice match.
Yeah, and especially the active regions like the group shown here, and we'll also have a group of active regions as is shown here, and there's several things probably here in the right, and a very similar thing here. And so if we can move to the next image that is combined UV.
This one?
No, the previous one.
This one.
Yep.
Yeah, so in order to have a better glance at the temperature distributions in the solar corona, we're placing 3 different channels with 3 different temperatures together. So the RGB for each of the image is composed of 3 lines, that is 211, 193, and 171. And 211 has the highest temperature, and the 171 has the lowest. So if we see the region that is red, it means that the temperature there is very hot. But for the blue region, it means that its temperature is probably below 1 MK, which is relatively cool. So,
yeah, when we say hot and cold, it's relative to the surface of the sun.
yeah, it's not comparable to our daily lives. Yeah. So, if you still remember the positions of the active regions, you're gonna see that the color of the active regions is yellow or close to the red, which means that the temperature there is probably below 2 million Kelvin, as I'm pointing here. But if you move to the coronal holes at those long channels, very thin channels, and it's blue, which means that the temperature is relatively cool. And if we're outside of the disk and say, for example, here, so this region has a color of red, which is very obvious, so its temperature is extremely hot, and it's basically that we have a active region here at the bottom, the surface, and there's very strong heating there, and heat up the energy and the temperature, so that's why we see the red color here. And we also get the red here and some cooler plasma here, maybe here, and it gives us a very clear distribution of the global temperature distribution.
Very cool. And this is all the simulations that were done yesterday for this final one-day forecast.
Yes.
Yeah. Very cool. Very cool. I was very encouraged by this morning waking up and you shared these comparisons between the model and Solar Dynamics Observatory. These are good comparisons. These are really, really challenging. Soho, Alaska. I'm sorry, did I say yes? Oh.
No, you were fine.
Oh, we're getting more images.
I was
my
passing
apologies.
images.
Yeah.
I was passing messages to someone else.
But these are extremely difficult simulations to do because there's so much uncertainty about the sun and our understanding of the complete physics. So it's a very impressive comparison.
Yeah.
Yeah.
We actually spent more than months doing with this project. So although we were only getting very, very hard for the recent days, probably after the beginning of the April, but we used more than several months to make preparation for the whole project. So the project is not just click and run the simulation. We need a lot of pre-processing, post-processing, and a lot of adjustment of the parameters in the model. So in our MGD model, we have more than 100 free parameters to focus on, and more than 10 parameters that is the most important that I can directly affect the white light outputs and all the observables. We've been using years to look into the adjustment of these models, how they can affect our outputs, different outputs. And so during the recent months, we were very tightly preparing for the magnetograms input for the model. We need to keep them aligned, make some calibrations, and we're also focusing on the post-processing. So after we get the model, we need to generate the observables from them. It's a lot of mathematical calculations, integrations, and a lot of codings and adjustment to generate the best images with the high qualities that can be compared to the eclipse images.
Yeah. Very cool. Do we want to transition to talking about impacts on the ionosphere?
Yes. We'll do a quick chair shuffle real quick. We can get Wei Hao in here. And we'll talk about one of the other aspects of what we've been working on the past couple months wasn't just modeling the corona, but was modeling the upper atmosphere of Earth, because when we block off our heating source, even for just a few minutes, we actually see some changes. So Wei Hao, do you want to walk us through that?
Yeah, as we know that the sun is the source of the Earth system, right? The sunlight drives the diurnal variation of the Earth. And to our common sense, since during the total solar eclipse, and the sunlight has been almost blocked, and then we can feel like it's very cool and the temperature a little bit drops down, right?
Yeah, it got a little breezy out there.
Yeah, so we can just feel almost the heat coming from the cement on the ground, something like that. And actually here, the science question is that how the total solar eclipse affects our Earth system, and what is in its effect in the ionosphere and upper atmosphere. Well, actually, I think just give a very short introduction of thermosphere, ionosphere. What is that? So I think ionosphere and upper atmosphere or thermosphere is just the top of the atmosphere we usually talk about. And
we
in
should
the-
all definitely know this because
Yeah.
Amy Weihao and I are taking
True.
ionosphere this semester.
Yeah, so in this spheres, the oxygen concentration is drops a little bit, and it gets the neutrons get weakly ionized, and so that's why we called it ionosphere. And on top of it, the neutrons and plasmas will get more ionized, and that's what we call it magnetosphere. And we can show a little bit results later. But here, this is the result we showed to simulate the ionospheric and thermospheric response to the total solar eclipse. And on the left panel, you can see that we applied the what we call the eclipse oscillation factor (EOF) to describe to quantify the residual EUV flux. So once the EOF is 0, that means that the UV flux is completely blocked by the moon, yeah.
And to clarify, the EUV flux means the changes in the extreme ultraviolet that we're seeing.
Yeah. So so here once we can we can see that as the time evolves, the sun, the moon is blocking out the sun, and then it gets recovered. So that's basically tells us how the sun is blocked and what happens during the total solar eclipse. And in the right figure, you can see that this is basically tells us how the temperature and the horizontal winds in the at an altitude of almost like 3 kilometers in the upper atmosphere and ionosphere, and how it responds to the total solar eclipse. And actually, you can see that there's a path going from the southwest to across the United States and to the
following the path of totality.
Yes, and here you can see that in the upper right panel, the temperature drops. Well, actually, that's the common sense, right? Because the sun is blocked by the moon.
Yeah.
So that will have a dip in the pressure, a thermal pressure, and then the wind will be like driven to that dip, the temperature,
That
dip in
vacuum
pressure.
of where we get that colder temperature, the
Yeah.
warmer wind is gonna flow in.
Yeah, and flow in, and that's why we can see that in the in the lower right panel, that there's a strong like the wind coming from the boundary to that slot of the totality. So this is basically tells us how the ionosphere and thermosphere responds to the totality, the total solar eclipse. Well, this is made by the GITR model, the global ionosphere thermosphere model. Yeah. So it's also in the space modeling framework at the University of Michigan.
Yeah, so the upper atmosphere model, GITM, that you said, is also requires supercomputers to run, so.
Yes, and actually this is made by, I think this is, it takes lots of time to run that model. So this is made yesterday and also based on our results. So we very acknowledge the supercomputer resources by Frontera at UTA.
We used a lot of computing power this week.
Yeah. That's it.
And this one will obviously take longer to get observations to compare to, because we're talking on a global scale, but.
Yeah, you can see that the map is the global scale.
We just received some preliminary observations from Detroit Observatory.
Oh, fantastic.
I'm putting them in a slide currently.
Let's get those up.
So I'm going to go back to
I will have to crop
you
them
guys
a
on
bit,
camera
so we
for a
still
minute
have
while we work
some
out.
time before we do that.
Pardon?
I still have to crop them a little bit,
Oh, okay.
so we still have some time before we do that.
Okay,
Just
we'll go
remember
back
that.
to the we'll go back to these results. I jumped the gun there.
Yeah, so I think just to clarify again, so the SWMF, the Space Weather Modeling Framework, is just that. It's a framework for a bunch of other models that we can input and change. So for instance, for our coronal models, we were using AWESOME-R.
Yeah, that's the module in the solar corona, what we call SC part in the SWMF code. And here what we use is to couple the inner heliosphere. So inner heliosphere means that how the solar corona infects the from in the interplanetary space from the sun to the Earth, and then we have the IH, what we call the inner heliosphere outputs, and put into the GitHub, and then this is the results run by that module. Yeah.
It's a very unique piece of technology that our group has to be able to not only, to be able to go, as we say, sun to mud and really perform these simulations from the solar surface down to the Earth's surface, and to make these forecasts before the eclipse happens, to understand to predict the shape of the corona, to predict the impact on the upper atmosphere is really exciting science for us.
I mean, that's what we're constantly doing as scientists, is we're making a model and comparing it to observations and hoping that we were right.
And right now we have Chip and Amy whittling away on initial results over here. It's just
I'm over here.
Sorry to
no, it's great.
waiting so soon.
It's digging in. We're all like really excited to see it.
Do we want to walk through some of our other models that we have ready to go? We kind of recapped them already, but if we can walk through them again.
Oh, the predictions we made?
Yeah.
Oh, sure. That's right on here, so we can.
We kind of talked about the EUV, but.
Yeah. This slideshow has been building up with data and results.
Yeah, so I think something that I kind of want to ask, not just you, Wayhouse, and you're in the hot seat though, but this is also directed towards John, you and maybe Chip, if he's not too busy with the Detroit images, but the differences between our white light predictions and our polarized brightness predictions.
They're going to be pretty similar. They're just, typically the PB brings out a little more structure. Again, it's the difference between two polarities. One is along the line of sight and one is in the plane of the sky. So that's basically the direction of the electric field in the light.
So real quick, I want to interject with an excellent question we just received from the chat. Dantix1 says there's a lot of observations being taken. What kind of equipment do you have pointed at the sky over there? I imagine it's something more beefy than a Google Pixel.
Well, you'd be shocked. We've just pointed our Google Pixels at the sky.
So the deeper answer to that, which it's a really good question, is that we had a lot of discussions, especially back in the summer. Chip and I sat down and started thinking about what we wanted to do with this project, and originally we were talking about how much money could we fundraise from different funding agencies, NSF or NASA, to support an observational component of this team. And unfortunately that didn't materialize, and so we had to be kind of budget conscious and careful. And so we started reaching out to other teams who were doing these observations, because in town here in Dallas-Fort Worth area, there's been a huge influx of scientists, both professional and amateur, taking images.
We have the Maverick field over on the other side of campus here at UTA is actually just filled with a bunch of astronomers, although I do think some of them were a little bit scared about the clouds.
Yeah.
And did ditch town to go to Arkansas, so.
Yeah, there was a bunch of them that hit the road this morning. So what we learned is that we reached out to many of these people who were very generous with their time and willing to talk with us, but what we learned is that there's a lot of processing they need to do with their images before they can have confidence enough to share them.
One of the people that we have been partnering with, ACES, they're looking at a time scale of 6 to 9 months. But we're also talking not just white light images, we're talking spectral lines that we're looking to compare further down the line.
So yeah, while you're asking about what other data there is, we're right now in this room sitting on pins and needles waiting for those first look images to trickle over to us and to hit the web. So the Google Pixel is not a bad starting point, all things considered. What we're trading in quality of image and capability. We're gaining in speed, being able to capture that image in real time and look at it. So.
Yeah, because Google Pixels in the 2017 eclipse were not anywhere near as good as they were today.
So, are you guys
we have them up in the slide deck.
Okay,
We
here
have
we
one
go.
of the images.
Yeah, anybody, okay, so we're gonna scroll over. What slide is it?
I believe let me double check. Sorry.
We're zipping through, we have all these slides worked
Slide
up.
18, last slide.
The last slide? Oh, I need to, give me 2 seconds, I need to refresh this, I apologize.
That's fine. Well, can we go to,
Oh, there it
I've
is.
been scrolling Instagram as well for amateur photos of the eclipse. I don't know if we're at liberty to share those with a handle.
Yeah.
What do you think? Okay. I can also put those in the slide deck.
Get on out of here.
Thank you.
So, yeah, here it is.
Oh wait, I'm looking at the delay. I was like, we've seen this before. Let me pull that up. I really want John Yu, Wei Hao, and Chip's input on these observation comparisons. So this is from Detroit Observatory, who we were talking to earlier this morning, who is actually the observatory in Ann Arbor with the University of Michigan. So great talking to some folks back home. But so on the right is our forecasted predictions for today, and on the left is Detroit Observatory's very preliminary results. I'm sure they're going to spend the next couple months really honing that in, but initial thoughts?
I can kind of two quick things to add to this. One is on the left, this is one of the reasons that these folks are a little hesitant to share it with us, because the processing they have to do to get the depth of brightness and see all the structure takes a bit of work. But that aside, what's really exciting to me is this little dot here, this little red bit, is this prominence that you could see with your naked eye when we were out on the field, which blew me away. It was this bright red spot, and you could see the arch just barely. And we see a corresponding arc towards the inner boundary of our simulation, and we also, adjacent to that, we see this bite out, this fast flow, cooler, less dense spot, and we see a corresponding bite out in the image. So that's what strikes me right away.
We even saw that in Amy's image.
Yeah, for sure.
But just real quick, what can y'all explain the difference between a solar prominence and the streamers that we were talking about earlier?
Well, a solar prominence is basically a dense condensation in the low corona. So it's typically 100 times denser than the surrounding corona and 100 times cooler. And it's dense enough that it has significant emission in this H alpha line, which is why it's called a prominence, because it's prominent over the limb of the sun. And so right, it's going to appear bright red, which it did, and they vary a great deal in size. There's active region prominences, which are pretty small and low down in the corona, and then there are the granddaddies, which are the polar crown prominences, go all the way across the sun, but near that coronal hole boundary. And those can lift off in spectacular eruptions.
Yeah. They were also a little bit speechless, not just from these results that we're getting, but also just from witnessing totality of, an hour ago?
Yeah. I mean, for a first look image, this is a pretty encouraging comparison.
Oh, absolutely.
Yeah.
And there's the enhanced brightness too in the upper left-hand corner, which corresponds quite well. So there's definitely something there.
And this is the ADEP map?
Yes.
Yeah.
The one we've been comparing to.
Yeah, it's our favorite child at the moment.
Wow.
So is there anything from the Detroit Observatory image that you're concerned about that's not showing up in our model? I mean, I know it's still a preliminary result, but because there's definitely that darker structure on the top right, but I feel like that could come out with further processing of these images.
Yeah, it's pretty saturated in terms of the observation, and I'm sure there's a lot more structure they can bring out with processing.
This is really cool stuff.
Yes, absolutely.
This is really cool stuff. We're really happy here.
Do we want to compare to Soho or Lascaux?
Are we ready to do that?
They do not have the time we're looking for quite yet.
Oh.
So I was looking through it. They only have up to, I'm not sure the exact time, but earlier today.
Yeah, they take a little bit
Yeah.
of time to get images uploaded.
Yeah, so I'm keeping an eye on that. I found some citizen science sort of images on Instagram, so more amateur comparisons. Maybe I can tag them and put them
Absolutely.
That would be
in the
fantastic.
slideshow as well.
Yeah.
I have one ready, and then I'll keep my eye out for the rest. Also, Shenyo, if you want to adjust the image so it matches your results, would be awesome. I'll go ahead and throw it in
Yeah.
there now.
The one that's ready, is that, what slide is that?
I don't have.
Oh, you don't have it up
ready
yet? Okay, no worries. Wow.
That's really promising first looks from the Detroit Observatory.
Yeah, it looks great.
It turned out really nice.
Yeah.
Yeah, this is a pretty big deal for us. Yeah, if there's any more questions in chat, I'm gonna sneak over to the hot seat for a little bit here, so you're not so lonely on camera. If there's any more questions in chat, we're really happy to answer them. We're processing things in real time, so this is kind of a look into what it's like for us at one of our most exciting moments. But there are a lot of times when we're doing these simulations on supercomputers and you're waiting for hours, days, weeks, and when you finally get the numbers back and you plot it and compare it to real observations, it's a pretty exciting event, and this is a big one for us.
Actually, that's a great question to ask, is how long in total did some of these models take to run?
I would say that for one model, it takes like 2 hours for the run and additional 2 hours for the data processing and preparation for the input. But we're not just running one model. So for each day of prediction, we're making 4 models, and to get the optimal output of the 4 models, we need to do some adjustments. So it could be more than 4 models. I would say like 10 models each time. So we're gonna using all the computational resources we have, running them all the time, and it's probably taking like 12 hours, say more than 2 computers for the host, for all the simulation outputs and inputs and everything for just one day. And we have several days, so we have several times of more than 12 hours of working in just one day.
Yeah, we've had 4 predictions in total at this point.
Well, 4 predictions 3 days ago, and those same 4 predictions repeated.
Not just those, because we did 7 3-day, and then we had one in March too as well. Our very preliminary model run.
It's hard to overstate the effort that went into this, because there was so much analysis and experimentation.
Parameter changing.
Yeah, with the model too.
Actually, not to throw another thing on your workload, but can we try to get some of the model comparisons over time, like the 7 3-day?
Oh, that's a really good question. I don't know if I have all those, but give me a minute.
Actually,
and
I might pass that over to Sean your way, how to try to get up as soon as we can.
Yeah.
I don't even know where our old model predictions have gone.
Oh yeah, that's also saved in our shared Google Drive.
Yeah, can you upload those to one of the PowerPoint slides, please?
We can do it right now.
We had another really good question. This is a really good question, actually, and this is one we're going to be able to talk about for a while. Dantix1 says, how far ahead are you trying to model? Forecasting weather just on Earth gets precarious for the further away you try to predict. It's probably the same for the sun, question mark?
So before you dive into that, I feel like I should point out this is one of my good friends. Asking all these great questions.
We got a ringer in chat.
Yeah, we do.
They're good questions.
But yeah, no, I mean, yeah, even terrestrial predictions get pretty hairy. I mean, cloud predictions is notoriously difficult. In fact, most cloud predictions weren't kind of finalized until a couple hours ago for totality. But one of the particular difficulties with predicting what's going on with the surface of the sun is that we don't always see the surface of the sun. It rotates and goes behind our view. So part of the difficulties at the start of this was actually how do we take current magnetogram maps and model them out to a few days in the future after it's rotated behind our view and come back around. Part of this whole project is looking at our models and saying, well, how correct are they, right?
Yeah. and I'm zipping through some slides. I'm not seeing exactly what I want to see as I'm trying to find some images to help describe this some more. So for this project, we specifically targeted a week in advance, 3 days in advance, and 1 day in advance. And those values were picked. On the longer forecast, you're trying to predict how sunspots are going to evolve as they rotate with the sun. The sun rotates every 28 days, and the surface is fluid. Oh, that's the slide.
Different presentation.
Different presentation. I will give you $1 if you drag and drop that slide into the current one. I'm so sorry.
Wow, I'm getting paid the big bucks.
That's
here.
right. Hey, come be a scientist. You'll never have to worry about putting $1 in the snack machine.
Oh. Well, I might not be getting that $1.
So we'll have this image up for you in a second, but so in the longer term, the harder it is to predict how the sun's surface is changing. After that, the big problem becomes, and I will pull this up. I have to make it visible. Thank you, you're a genius.
That's why you hired me.
That's why I hired him. So let's do this. There we go. So this is kind of shows the process of our forecast. We're starting with what's called solar magnetograms that tell us the polarity and the strength of the sun's magnetic field. Forecasting it days into the future is the process of using simulations to rotate that and let it flow into the future across the surface of the sun. And then using a model called AWESOME or AWESOME-R to determine how, as this material heats and tries to escape from the sun, how magnetic field holds it back in some places or allows it to flow out in other places. Now that's the part that's extremely challenging, because until the eclipse happens, the amount of data we have to validate that is extremely
very limited.
So the advantage you have in climate and weather forecasting is a much more data-rich environment. I'm sure if we talk to weather and climate people, they'll be like, never enough. But
we also say never enough,
yes.
but we have far fewer observation points than they do. I mean,
Yeah.
any Joe Schmo can go stand on a mountain and go, oh, there's a cloud. Oh, it's raining. Well, we can't really send Joe Schmo out into space.
I mean, we can, but it's just lawsuit rich environment. So
that one really got chipped.
yeah, it should be. So in a lot of ways we've been flying blind, and the research team, who I'm going to highlight again over here, has been doing these simulations and just doing very rudimentary comparisons to see if we're even in the ballpark. Yeah. So to be able to come back today and see these early, oops, I have to go to the right spot in the comparisons here, to see these early data model comparisons. Oh, that's wonderful.
Oh, is this the one from Instagram?
Yes.
Wow, that's a really good comparison.
Yeah, reload it so you get the handle.
Oh, yeah.
Wait.
Let me go back here, and I will pop out. And we're putting this up as fast as we see them. There we go.
You can see a lot of prominences. I don't think I remember seeing that many.
Oh, there's a whole bunch of new slides on there. That's really great.
So I also kind of want y'all's reaction to these image comparisons as we're going. So we're on slide 20 right now, looking specifically at those solar prominences that we're seeing. How do those translate to our predicted white light images? I think they're still sinking it in over there. But while they kind of like look at these real quick, so to kind of answer your question, we don't know. We're testing that out in real time right now.
Yeah. Now, I will say there's a whole separate subfield, and this is where Catherine, Amy, and I are a little more
Yes.
much more experience compared to solar forecasting, of just trying to understand once this material escapes from the sun and heads towards the Earth, how it impacts the Earth system. And that is, again, a very challenging, young field.
Very young.
And part of this, we're going through the process of the growing pains of learning all the lessons that climate and weather people have done so far.
But thankfully that means we get to point at them and go, oh, hey, they did it this way.
Exactly.
So, Chip, what do you think of some of these preliminary images that we're getting from social media?
Fantastic. Yeah, so people really know what they're doing. I mean, they're at very high resolution, and they have the exposure very well timed to bring out that structure deep down in the corona. It will be interesting to see these prominences form exclusively along what's known as a polarity inversion line, typically found in active regions, but they're also found in quiet regions as well. So it'll be interesting to see with our magnetic maps if we have that quality, that polarity inversion line, where these filaments are being seen. We don't have the physics really in the model as it is to capture and resolve these. Well, we have the physics, we don't really have the resolution just deep down in the atmosphere to capture a filament, but the magnetic structure should be present.
This is really cool. And then I'm gonna jump back. Oh, look at this one.
Yeah, Amy, if you could go back to the slide before.
So this is, I'm trying to read their name, Byron Haney Music on Instagram. Some of these are really promising. Oh my gosh, like.
Yeah, so Johnny, what do you think of how this one's comparing to, again, I'm assuming our ADAPT model?
This I would say that the comparison is really, really good. And you can see that the structure is much more clear in its image. You can see the streamer in the upper left, in the upper, and in the bottom left, and a whole branch of magnetic field lines stretching out in the right bottom, and very strong enhancement of the white light in this region. And I would say that our model has successfully reproduced all these kind of structures in our white light image showing the left, showing the right. So for clarification, so the figure in the left is the figure from the observation, and the right is showing our model output.
So good. And then the other slide I want to jump to real quick, thank you guys for putting this one together. This is how much the forecast changed from the team here from 3 days ago, April 5th, to yesterday. And this is a big this is a surprising, like, I kind of went to bed last night thinking about, well, you know what, it can't be that different.
I was thinking the same thing, but.
And now that you see it, it's like, yeah, there's some pretty significant shifts between these two pictures.
Do you guys want to highlight what some of those shifts are?
I would like to talk about more about the UV images that is in the next slide, I think.
Yes, absolutely.
Yeah, so here we're showing the model output from our 3-day forecast that is made on April the 5th, and our 1 day of prediction that is made yesterday. So we can actually see a lot of differences, especially those structures in the disk. So if you can see the 2 arrows pointing to the outer region in the two figures, we can see that in the first figure, the outer region is not so strong as the outer region in the second figure. And this is basically that when we're still 3 days before today, when we're still getting the first model, that outer region was still near the very edge part of the sun. And we're not having a good observation of it, so we don't have the magnetic field data. We didn't produce a very realistic distribution of the thermodynamic structure in that outer region. But now, as the sun is rotating, that outer region is coming to the center of our field of view, so we get a better observation yesterday, and we're able to capture the fine structures in the magnetic field and produce a realistic outer region and the temperature and density distributions, and produce a stronger outer region in the center.
And where you have merging there, that's
That's like so it's like the actual region is merging out from our 3D of to the 1D of.
Yeah.
That means we have a better understanding of that natural region.
Yeah. Very cool. Very cool stuff.
That is shocking how much it changed between just our 3-day and our 1-day forecast.
Yeah, that's quite impressive.
I guess that kind of hones in the point that the sun is constantly changing.
Yeah. For sure. Oh my gosh.
Well, unless we magically get some more observations in the next half a second, I think we're gonna actually go ahead and wrap up here. I guess just final thoughts from everybody in the room, both about how well our model predictions went to how you felt getting to see totality today.
We gotta bring our man on the street here.
How did you feel seeing totality?
It was very, very neat. I would recommend, if you somehow have one near you, definitely go see it.
Well, unfortunately, the 2026 eclipse is mostly going over the Arctic, so that will be a quick drive.
It's a nice vacation spot, you know. I heard they have great weather this time of year.
I heard it's warming up. So I guess any final comments from all y'all?
I'm just so happy we got to do this. I'm really excited to be able to compare to more refined observations. This is very cool stuff. What about y'all?
Yeah, I'm also looking forward to seeing the observational images to compare with our models the further way. Yeah. Also, I think it's I would say the best time of in my life.
Oh wow!
Like here, up to now, like it's very fantastic.
It's because of all the Mexican food we've been eating. No, totality really was. I mean, they talk about it as it being a life-changing experience. It really was spectacular.
Yeah, it's so hard to describe how much you lose in the images that we're showing compared to when you take those glasses off, and it's a lot. Yeah. And if I could just leave with the thought of, Chip Udit and I approached you all and to be part of this project, and all of this is far more than I hoped it could have been, because you all worked extremely hard on this, and I'm very proud to just play a supporting role here to a bunch of people who could make this come to life. So that was great.
And also
Thank you.
give me $1.
And I do owe you $1 for yeah. Okay, you want to wrap us up?
Yeah, sure. So thanks so much for joining us throughout the day. This has been Coronacast 2024. We will continue to update our website with results and later publications that we make as we continue to compare our model outputs to observations that have been made today. Again, thank you so much for joining us, and have a wonderful day.